World War II was not just a war of soldiers, but of machines. In the skies over Europe, a hidden battle was being fought, a battle of engineering, horsepower, and innovation. This was a war of engines. At its center was a British masterpiece, the Rolls-Royce Merlin. It powered the Spitfire and the Hurricane, but it had a weakness. It choked in the thin air of high altitudes. The engine's fate, and perhaps Britain's, rested on one man, a brilliant engineer named Sir Stanley Hooker. He saw what others didn't, supercharging the Merlin and transforming it into the high-altitude Titan that would dominate the skies. But Britain couldn't build them fast enough. The call went out to America, and the Packard Motor Company answered. They built over 55,000 Merlins, giving the legendary P-51 Mustang its wings and ensuring Allied air supremacy. Yet, as the Merlin roared to victory, another British visionary was quietly changing the future. In April 1937, long before the war began, an RAF officer named Sir Frank Whittle created a radical, almost unbelievable invention, the turbojet engine, a screaming new power with no pistons, no propellers. It was the dawn of a new age. And in the darkest days of 1941, Britain made a decision of staggering importance. They put their most precious secret, the prototype jet engine itself, on a plane and sent it to the United States. It was a gift of trust, an act of faith that would shrink the globe and define the modern world. And it went on to power not only the first British jet fighter, but also both the United States, the Lockheed F-80 Shooting Star, and Russia's, the lethal MiG-15.
In an age when the fate of nations hung in the balance, one man engineered the thunder. This is the story of Sir Stanley Hooker. From the Spitfire's cry to the Concorde's boom, his engines powered the fastest machines of their time. But his greatest triumph was forged in Britain's darkest hour.
I think my greatest success was the two-stage supercharger on the Merlin. That I did do myself. And I proposed it, I specified it, I did all the calculations, we made it, and it worked first pop. It puts 70 miles an hour on the speed of the Spitfire and 10,000 feet on its fighting altitude. Air Marshal Gordon flew the first one, always tells me about how he soared up past an FW-190. He said I could see the German pilot following me up like that with a look of utter astonishment on his face. So, without any doubt, I think the two-stage Merlin, which was my first real contribution to aviation, was my best.
Stanley was showing by his supercharger technology how to stuff the air through the engine. And the Merlin power was increased from 1,000 horsepower at the beginning of the war to 2,000 at the end of the war. And by these means, the RAF was able to keep ahead of the Germans. If it hadn't been for that work, I don't think the RAF could have won the Battle of Britain.
Stanley Hooker was born in 1907, the son of a Kent farm manager. He was quick to demonstrate a gift for physics and mathematics. By the age of 28, with degrees from Imperial College and Oxford, and in danger of becoming a professional student, he took a scientific job with the Admiralty. But his engineering career came about by chance. By the late 1930s, the great rearmament program was underway. Aircraft factories were being built across the country. There were thousands of jobs going on the new production lines, and bright young boffins were needed in the design departments. It was at this time that Stanley Hooker first met Ernest Hives, the formidable boss of Rolls-Royce's Derby factory.
Well, it was in January 1938, early in January 1938. And I remember on one of the usual miserable, cold, dark, damp days, when I walked up Nightingale Road in Derby to be interviewed by Lord Hives over there. And I remember wondering what the hell I was doing there, because I had a very nice job in the scientific research department of the Admiralty at the time. And I went into old Hives' office, and he had all my papers on this very desk. This was the desk in question. And he's thumbing through these because I had a degree in mathematics from London and a doctorate from Oxford, and I'd written quite a lot of theoretical papers on aerodynamics primarily.
Mm-hmm.
And he thumbed through all this lot, and he looked at me and he said, "You're not much of an engineer, are you?" I said, "No, I'm not." I had to admit that. He said, "Never mind." He said, we can teach you to be an engineer." And he said, "Who do you work for? Who do you work for?" And I said, "Well," I told him. And he picked up the phone and said to his secretary, "Get me Sir Charles Wright," it was at the time. I thought, good God, I hadn't told the Admiralty I was going there for a job or anything of that kind. And I thought, well, he's going to cut the ground from under my feet now. And he did too. He rang this fellow up and they had a conversation on the phone. And he said, "Well, he says you're a dirty dog because he's just promoted you." He said, "But we can have you if we want to." When I arrived, they led me through this hurricane of activity that went on in Rolls-Royce, telephones ringing, typewriters clapping, great big drawing boards and that sort of thing, to a little office with glass partitioned office, opened the door and there was an empty desk and a bookcase and a telephone and a chair. They said, "This is your office, cheerio," and he left me. And of course I sat there all day and did nothing. Next day the same thing happened. Third day I took the Times in with me and took my pipe and started to smoke, because smoking was forbidden, except between 10:30 and 11 in those days. But I started to smoke in the morning and people came up to me and do that. I thought, oh, hell with you, nothing else to do. So I went on smoking. And eventually I got tired of this, and I went out of the office into the next office, where there were a lot of young men, all busy as hell with drawings and calculations and so forth. And over in the corner was a very quiet old boy, grey-haired, and sitting rather active. It was after lunch. I think he was asleep, actually, sitting like this. And I went over to him and I said, "What do you do?" And he said, I'm in charge of supercharger testing." So I said, "What's that mean?" Well, he said, we put a supercharger on an electric motor rig and we test it and we measure the pressure and the airflow and all these characteristics. He said, "And here's the results." And he showed me. I said, "Well, can I have one of those curves?" And he said, "Oh, have the lot," like that. So I went away to my office with this bunch of data, which was meat to me because I'd been trained to handle the flow of air and pressures and temperatures and so forth. And I analysed all this lot and came to the conclusion that there'd got to be certain changes made in the compressor if it was, although I'd never seen one at that stage. I'd never seen an aero engine close to or a supercharger, but one could deduce what the diffuser efficiency was, the rotary efficiency and so on. And I did this and I wrote a report. And I didn't hear anything about it, and I passed it to the chief engineer, who looked at it and said, "Oh, this is very interesting, I must pass this to Mr. Eller," who was the chief experimental engineer. And about a week later, old Eller burst into my office. I was just going home. I should leave at 5 on the dot with nothing else to do. And he waved this thing at me. He said, "Did you write this?" I said, "Yes." So I thought, good God, what happened now? He said, "Well, you're in charge of superchargers." And that's how I got my first job. Well, the day after war was declared, a Monday, was the usual day in which Hives held his great technical survey of the position of the Merlin engine, principally at that time. And I remember him coming in to the meeting, sitting down and looking at it all and saying, "Now, we're in this war and we've got to win it. No good being a good second." And he immediately set about the usual agenda for the afternoon. Of course, Rolls-Royce were already set up by Hives to double their output overnight. It meant the men had got to work a lot harder, of course, but the machine tools and the materials and everything were there, ready for that. In fact, the men worked 18 hours a day for 7 days a week when the war started, because every engine that fought in the Battle of Britain was actually made at the works at Derby. There was no other factory in the country producing Merlin engines at the time.
The atmosphere at Derby in 1940 was intense because the war was on the go, and the engines that we had in the Hurricane and Spitfire, Rolls-Royce engines, were smaller than the German engines, and we therefore had to produce as much, if not more, power than the Germans from a smaller engine, and that meant a more high degree of development.
And so we were able to advance the power of the Merlin all through the war steadily, from 1,000 horsepower to 2,000 horsepower, without basically changing the engine. It still went into the Lancasters and the Hurricanes and the Spitfires, the Mosquitoes, no basic change. Whereas the Germans had departed and built the Focke-Wulf 190 with a great lumbering air-cooled engine in it. Brute force and bloody ignorance, I called it at the time, I remember. And we were all obsessed by the idea that we were going to keep the Merlin ahead of the Germans. And we did too.
By the summer of 1940, the piston engine fighters were flying in the Battle of Britain, while on the ground, in a disused foundry, a top-secret design was being developed, Frank Whittle's jet engine. But his radical idea had few supporters. One of them was Stanley Hooker.
And I had several times tried to persuade old Hives to go and see this engine. And he said to me, you know, what does it do? And I said, well, it gives 1,000 pounds of thrust. He said, 1,000 pounds of thrust? He said, what's the use of that? So that wouldn't pull the skin off a rice pudding, would it?
But Hooker knew the power was there. He would prove to Hives that Frank Whittle's jet was worth investigating.
And so on the Sunday, he picked me up in his car and we drove down and we saw Whittle's engine running. And old Hyde went round without any comment, very much comment, and Whittle was telling him all about the engine, the advantages and so forth. And at the end of it, old Hyde looked at Whittle and he said, I can't see many engines about here, Whittle. He said, where are they all? And Frank Whittle said, well, I've only got two, you know. He said, I can't get the parts made. So old Hyde said to him, send us the drawings, we'll make bits for you. And we did.
But the Ministry of Aircraft Production had already chosen the Rover Motorcar Company to make the early Whittle engines. By 1942, though, Rover's management and Whittle were barely speaking. Hooker heard about the conflict and told Hives, who began to plot. He wanted to make that remarkable jet engine. And he did.
And one day old Hives said to me, come on, we're going to have dinner with S.B. Wilkes, the chairman of Rovers, at Clitheroe tonight. So away I went with him. I didn't know what was going to happen. We had a nice dinner. The Pride Bob won. But being Yorkshire, you get a bit over the odds, you know. And we had a very nice dinner. When dinner was over, old Hives turned to Welsh and said, no, look, he said, Welsh, what are you doing with this jet engine? He said, I hear you're not getting on with this chap Whittle. And old Welsh said, no, we're finding him very difficult. So Hives said, well, you shouldn't be doing that engine, should you? You're not an aero engine company. You grub about on the ground, I remember him saying. And he said, I'll tell you what I'll do. He said, I'll give you our tank engine factory at Nottingham. You give me this jet job up here. And old Will said, done, I should be jolly glad to be shot at the job. And that's how we got Barnoldswick and the development, and we became responsible for the production of jet engines.
We were mostly young men. Even Stanley Hooker himself would only be 35 or 6 at that time, and he was the boss. I myself was 30. We had a complete carte blanche to do almost what we wanted with regard to modifying the engines. If we thought up some new way of constructing it that could be done without too much manufacturing, we used to get tests done overnight, and we'd have tested them in the next day. If it required manufacturing, we had all the resources of Rolls-Royce to call on to get casting, sheet metal work, and that sort of thing. And so we could do quite advanced things in a matter of weeks.
Few believed the jet would be powerful enough, but Hooker and his team proved the doubt is wrong when the Meteor jet became the first plane fast enough to shoot down a flying bomb in 1944.
We went on developing the engine, and then we were told by the ministry to design an engine of 4,000 pounds of thrust, which is a big step up, twice the thrust. And I was sent to America about that time, because we had great collaborations with the Americans. We told them everything we were doing. And they even had a Whittle engine. He gave them an engine. And to my horror, when I got there, I found they were already running an engine at 4,000 pounds of thrust, or close to. The General Electric company were. And so when I came back, I said, to hell with this 4,000, let's design it for 5. And we rang up, I remember ringing up the ministry, George Watt, and Group Captain George Watt was in charge. I said, look, George, we're forgetting 4,000, we're going for 5,000. He said, okay, and that was all we had to do in those days. Now it would take a year to get a thing agreed like that. We started it in January 1945. We had it running by the middle of the year, and we took the world speed record in October the same year. It was the first aeroplane ever to exceed 600 miles an hour with neutral.
We were improving rapidly a new breed of engine. We also began to see that it would revolutionize air transport altogether, not just as a fighter engine, but in transport aircraft and everything. And I would have thought that Stanley Hooker was one of the first people to see that this would be so.
The Rolls-Royce workshops at Derby have been producing air record-breaking engines for almost 20 years. It is here that the famous Derwent jet engines are made. Engines that can hurl a plane through space at a speed where the normal smooth flow of air breaks down into a series of violent shock waves.
But a shock wave of the personal sort lay ahead for Hooker. One of his projects, the Avon, went wrong, and he quarreled with his mentor, Hives.
He said, there's too much hanging on the fate of this Avon engine for me to leave it up here in this damn garage. He said, this isn't Rolls-Royce, you know, he called it a garage. This isn't Rolls-Royce. Rolls-Royce at Derby, I'm going to take it there. And I said, what are you going to do with me then? He said, well, I think I'm going to send you home for 3 months. So I said, well, that's a fine return for 11 years hard work with you. I remember saying that to him. He said, I don't care about that. He said, you go home. He said, where are you going? I said, I don't know. He said, what's your address? I said, well, I'm not going to tell you. He said, well, how can I get in touch with you? And I said, well, you can't get in touch with me. I said, if you want to get in touch with me, you ring my bank. I said, but I'll tell you one thing. If you send me home, I'll never work in a factory controlled by you again. And so we parted like that at Barnoldswick. And I must say, it was a very miserable and traumatic day for me.
The Rolls-Royce gas turbine team at Barnoldswick under Hooker had been enormously successful, of course, and one thought of Hooker as, after Whittle, as the most important gas turbine engineer in England, probably in the world. And when the Avon got into serious trouble and brought back to Derby, it was a bit of a shock to us that Hooker was given a comparatively small job.
Hives had persuaded Hooker to return and head Derby's research team. But the new job fell lamentably short of what Hooker had expected.
Hives had always promised me, he had promised me that I should be chief engineer of Rolls-Royce, you know. And by this time I was about 40, and I thought it was time I was made chief engineer of Rolls-Royce. Not like today, where, you know, at 50 you're a promising young engineer in Rolls-Royce. But in those days, I thought I was in charge of a turbine job when I was about 30, and by the time I hit 40, I thought I was ready to take over the whole damn firm.
But Hooker resigned instead. The Bristol Aeroplane Company was expanding into jet production and badly needed Hooker's expertise. Bristol had run into serious problems with the engine design of their new passenger plane, the Britannia. If they didn't get it right, and quickly, the company would collapse. Hooker's first job was to redesign the troublesome turboprop engine.
It was a time when I felt responsibility very heavily, because I felt I was the only man in the company who had any real experience of jet engines.
In the engine school, Dr. Stanley Hooker, the chief engineer, talks to flight crews from the Royal Air Force, Royal Canadian Air Force, and the Canadian Pacific Airlines.
For more and more horsepower. And so it is to the turbine engine over here that we have to turn for the lift of the car. These are the basic casings of the engine, opened up for your inspection, and over here we have the inside components which really produce the power.
Hooker ran Bristol's engine team in the exhilarating years when the government spent freely on new fighter and bomber projects. When the mighty Vulcan, the flying dart, needed an engine, Hooker was determined to make one more powerful than anything his old Rolls-Royce colleagues could achieve.
I remember sending out a Christmas card. We were very proud of this engine. It was the most powerful engine in the world at the time. very proud of it. And we had a picture of Mount Olympus on one side, and the Mount Olympus 9,750 feet. Picture of the Olympus engine on the other side, Olympus engine 9,750 pounds of thrust, you see. I sent this out, and I sent it to some of my pals in Rolls-Royce. One of them wrote back to me and said, "How does the weight compare?"
In 1958, the most expensive ever aircraft was ordered, TSR2, designed around the successful Olympus engine, the world's first strike and reconnaissance plane. The Air Ministry demanded constant changes. Frustration mounted on both sides as delays and wrangling blew costs up to an all-time high.
I remember saying to Geoffrey Tuttle when he was Vice Chief of the Air Staff, when they demanded 1,000 miles of radius of operation for the TSR2, I met Geoffrey Tuttle one day on an airfield, and I said, "Geoffrey, why 1,000 miles?" I said, "It sounds like a number just conjured out of the air." He said, "'Tis." He said, "It's an objective, 1,000 miles." I said, "Well, that will cost you £1 million a mile. For the last 150 miles will cost you £1 million a mile." Well, that was an underestimate, I guess, too.
Within a few years, the TSR2 had made its first flight and was regarded as a fighter of brilliant performance. Then, in 1965, with stunning suddenness, it was scrapped.
There was old Sands white paper in 1958 which said, "We're finished with man-piloted aircraft. We're going to have missiles. Press the button. No more men." So men were out. Then the Americans cancelled the missile, which was it? Bruce Streak or something. Yeah, they cancelled that. So we had no missiles, no manned aircraft. Old Thornycroft arrived on the scene, or Lord Thornycroft arrived on the scene, rather. And he said, "Well, I haven't got any airplanes, I haven't got any missiles on the stock. I'll order some more airplanes." So he ordered the supersonic vertical takeoff airplane, the Armstrong Siddeley airplane, the TSR2, etc. Old Healy came along, so manned airplanes were back in again. Old Healy came along and said, "We can't afford all that lot. We'll buy F-111s on tick." So manned airplanes red again. So in a period of a few years, we were in, we were out, we were in, we were out. It's more like a boat race than a policy to follow.
Hooker's highest hope for the Olympus now rode with a supersonic airliner, Concord. But it took 18 years development, with constant threats of cancellation, before Concord made its first scheduled flight in 1976. Through those years of controversy, first over TSR2, then Concord, Hooker had been quietly developing another extraordinary aircraft engine for the first vertical takeoff fighter, the JumpJet Harrier.
We had this engine, but of course there was no aeroplane anywhere on the stocks that I knew of to take it. And I must say we didn't push it all that much either, because I wasn't really absolutely convinced that it wasn't funny, myself. And we were very heavily involved in TSR2 at the time. But I got a letter from Sidney Cam which said, "Dear Hooker, what are you doing about vertical takeoff? Yours, Sidney." Sidney Cam was the chief designer of Hawkers. They'd made all the RAF fighters from way back in the 1930s. The Hart, the Fury, the Demon, etc., the Hunter, the Hurricane. And so I sent him a copy of our project brochure for the Pegasus, you see. And then forgot about that too. And a few weeks later, the telephone rang, and it was Sidney on the other end, and of course he was a very irate character, or could be, or made out to be. He said, "When are you going to see me, Hooker?" He said. So I said, "Well, I'll come any time." So I said, "What's the subject?" He said, "The subject," he said, "I've got an aeroplane round your engine." I said, "Which engine?" He said, "The vertical take engine, you fool, So of course up I went, and there I saw a picture of the P-1127, which is just like the Harrier, and there was the Pegasus engine installed in it. I said to Sidney when we first put it in, "I suppose you're going to do some conventional flying," because the aeroplane could be used conventionally. All you had to do was point the nozzle back, and it was just a normal aeroplane. "I suppose you're going to do some conventional flying first, Sidney." He said, "What for?" I said, well, you know, just to make sure the aeroplane's a nice aeroplane and everything under control. Oh, he said, the Hawker aeroplanes are always beautiful. He said, there's nothing wrong with the Hawker aeroplane, not going to bother with that. It's vertical first time. And they tethered it on the end of a piece of string, you know. And the result was that when it took off, it went zzz, like you know, all over the place, and it was very, very difficult.
The old British Harrier went on to become an international success. Hooker had believed in it from the beginning. His support never wavered. It was his tenacity that kept the project alive.
The world, Derby, America, the rest of the world have spent a mint of money trying to make a VTOL fighter, and not one of them has succeeded. It's still the supreme solution as a VTOL fighter.
The ultimate test of the Harrier's prowess came in the Falklands War, long after Stanley Hooker had retired. But without Stanley Hooker, there would have been no Pegasus engine and no Harrier. And without the JumpJet, there would have been no Task Force Victory. In 1967, Hooker retired to his country home near Bristol. By this time, his former employer, Rolls-Royce, had taken over the Bristol firm and was a main pillar of the British aircraft industry. But in 1971, the unthinkable happened. Rolls-Royce couldn't pay its bills. Edward Heath's government moved swiftly to prevent total collapse. They bought the company, except for the RB211 jet engine that had caused Rolls-Royce's downfall. So Stanley Hooker was brought out of retirement as the one man who could convince the government that the RB211 was worth saving.
The morale of the whole outfit, of the engineers particularly, had, you know, sunk to its lowest possible ebb. And there was a tendency to blame one another, you know. I think he ought to be sacked, or he ought to be sacked, and so forth, you know. And also I found that the first 11 wasn't necessarily working on the engine, which was a disaster. And so the first job I had to do was to try to get more people, better people working on the engine.
Hooker was back at the helm, responsible for the success or failure of the RB211 program. He brought in his trusted colleagues from the old days. Among them, Harry Pearson.
He had an enormous influence on the position. He put everybody's courage back. You know, they'd begun to lose heart. He restored that. And it was so typical of the man. He didn't find fault with anything. He just got down to it and made a wonderful engine, and what was potentially a good engine anyway.
I think if the RB211 had failed totally, it would be a terrible setback for British high-technology engineering. And Stanley came back from retirement. He took a grip of the engine and the engineers. He directed them, and he got it right.
The motivating thing is to make a good engine, a powerful engine, you know, the best engine, reliable engine, not to kill anybody and so on. That's the motivating thing. And most engineers bend their life to that task.
But times had changed from Hooker's early days, when it was the engineer whose word ruled. When he retired in 1978, accountants were in command.
And we used to start an engine by saying, well, what's the engine got to do? You know, that much. How long does it take us to draw it? That much. How long it takes to make the first experimental engines? How much testing have we got to do? When can they put it into production? And how much will it cost? So we start with, is it any damn good? That was number one question. Now it's the other way around. How much is the damn thing going to cost, you know? When do we put it in production? How many development engines are we going to have? How long is it going to take us to design it? The last question seems to be, is it any damn good? It's all gone round the other way.
Well, Einstein was a great mathematician, a genius. I always thought that Stanley was a near genius. He was very, very clever and a very good engineer. And very clever, very good engineers are very difficult to find. You don't get too many in a generation or in a country.
The roar of the Merlin may eventually fade, but the legacy of Sir Stanley Hooker, a relentless pursuit of power and perfection, forever changed the skies. He was a true titan of engineering.
Through the night of combat danger, this heart of power, the three engines of a patrol torpedo boat, could never stop. The lives of a crew of Americans depended on them. Facing an armored world with nothing but speed, the PT boat made a bet every time it roared into action. Bet you 10 lives I can get in, blast you, and get away before you can touch me. The Army rescue boat of the Air Forces raced against time, the seconds in which a downed plane sank, or the minutes it took to freeze a flyer in winter oceans. The Warhawk carried a single pursuit pilot who put his trust in it. British flyers swore by their Hurricane, nicknamed Can Opener, when its 40mm guns ripped open Nazi tanks in Africa. Members of Lancaster crews learned that engine failure on a deep penetration of Germany was the least of their worries. Fastest of bombers, the Mosquito made the Berlin run on speed alone. All planes returned safely was the communique celebrating their nightly triumphs. The Mustang, fastest of the fighters before jet planes went to work, climbed higher too. It wasn't as big as some, and it couldn't cook, but flyers fell in love with it. You can hear them snarling away up there and feel the hard courage. They can dive 40,000 feet and not get heart failure. Want to look at a heart like that? The power inside all 5 planes? There she be, the Packard version of the Rolls-Royce engine sitting on the test block, pretty as a picture. Strong as 1,500 horses, equal to the weight of one. Want to see the heart of an Elco PT boat, mighty midget of the U.S. Navy? Or of an Army Air Force rescue boat? This is the Packard Marine engine. It is a 60-degree V-12 aircraft-type water-cooled supercharged engine of 1,500 horsepower. The boys on a PT boat housing 3 of these say it'd fly if they opened the hatches. These engines have a home, the giant rooms of the Packard factories. They come into first being in the pouring hot metal of the foundry. The clangor of the forge is their birth cry. They are shaped in an intricately organized jungle of machinery, formed on the varied devices typical of the industrial might of America. Thousands of machines. The intimate touch is not lacking when a profilometer measures a skin or surface texture in millionths of an inch. These engines have parents, tens of thousands of them working around the clock, day and night. Young and middle-aged. War vet James Thornborough, invalided from the African campaign. And a war bride with a husband who saw action. And newcomer Steve Surowski, who still needs a guide to show him what to do and how. Here's Steve Komisiak, who's been with Packard 41 years. These engines have ancestors, a pride of ancestry, and a history dating from the early days. It was 30 years ago, in 1915, at the beginning of another war. A new world was bursting in upon a civilization that seems quaint to us now. Autos still remembered they had once been buggies, and the directors of a young auto company, Packard, looking farther ahead than they knew, decided to set aside $250,000 for the development of an aircraft engine. Here in the Packard Hall of Fame is what they came up with, Old 299, named from the cubic inches of its piston displacement. Since there were no facilities at that time for testing an engine in a plane, the famous auto racer Ralph de Palma was hired to see what it could do on the ground. It could do plenty. It could win 5 races in one afternoon in 1916 at Sheepshead Bay and establish records in each. Satisfied those principles were correct, an engine 3 times as big, the 905, was made. It broke the world's mile record at 149.4 miles per hour and ran 20 miles, averaging 134 miles per hour. Out of that engine, 905, came the Liberty motor of World War I, co-designed and built in volume by Packard. Then we were asked to build the engines for the Navy's first dirigible. They had to be able to run 300 hours without an overhaul instead of 50, the former requirement. The Shenandoah was bent on seeing the world with no stopovers for tinkering. We made a lot of engines in those years. Engine 1500, which normally ran upside down, powered Boeing 66, world's fastest standard fighting ship. We built the first engine designed specifically for a tank. Before 1924, any engine strong enough and sturdy would do for a tank. That same year, a Navy PN-9 with 2 600-horsepower Packards set 7 world and 20 American records. The next year, one of them flew to Honolulu, 1,841 miles, which was another record. In 1926, we wound up and delivered our 24-cylinder X engine, the most powerful in the world. Just then, an air-cooled engine took over American aviation. What's the difference? If nobody wants a liquid-cooled inline engine in the air, put it in the water and make a clean sweep of speedboat racing for a decade. The Gold Cup, the sweepstakes, and the Harmsworth races were by way of becoming the private preserve of Packard power. We were learning how close an engine can come to making a wingless boat fly. Miss America 10 set a world's record of 124.9 miles per hour. And that's about where matters stood when the World's Fair opened in Flushing Meadow. The world was at peace. At least we were permitted to think so for a little longer. The evening fireworks were very popular. Aerial torpedoes exploded so loudly you could actually feel a slight concussion. But the Navy was already working on an idea they called a patrol torpedo boat. It was a speedboat for fighting. And when the Navy called for an engine to put in this boat, Packard was first in line. It was more than 2 years before Pearl Harbor. Navy orders 7 Packard Marine engines. 7 months later, Navy orders 81 Packard Marine engines. 1 year to go to Pearl Harbor. Navy orders 720 Packard Marine engines. 5 months to go. U.S. Navy and Great Britain order 900 more Packard Marine engines. This was only Packard's pre-war beginning. Here comes a mighty battle wagon with a strange burden. The Rolls-Royce engine with a blanket permission to manufacture was being brought to the United States with maximum safety. Not content with one such problem of its own making, Packard in the summer of 1940 rushed in where others feared to tread. Only Packard thought this hand-fitted job of more than 14,000 parts could be mass-produced. Like the Marine engine, this baby has a history. It goes back to the first Rolls-Royce aircraft engine for World War I, 25 years ago. It goes back to the power plant of a slim racer, the British Snyder Cup entrant of 1931. This was the engine that beat the Luftwaffe against terrible odds. On September 2nd, 1940, 700 German planes rained fire, death, and destruction on London. The following day, Packard signed a contract to deliver 6,000 engines to Great Britain. The next week, a contract for thousands more was signed with the United States. How do you do it? How does Packard turn out 50, 60, 70,000 of these fantastically complicated engines, marine and air, in the following war years? You grow. You're a mile long to begin with. you grow fast. Ground was broken for this engineering and assembling a month before the architects finished their plans. 78 test cells invite 78 roaring engines to run their 6-hour tests simultaneously. Another mushroom of the so-called 10-month miracle of construction was the tear-down and reassembly building. The heat treat building was fourth of the new structures rushed to completion for the Rolls-Royce assignment. When the production ante had been upped a few more times, this new $5 million Toledo war plant was taken over to continue the expansion. Then Packard funds bought another Detroit plant 3 miles away. It added 150,000 more square feet of manufacturing space. And across the railroad tracks, a matter of blocks away, more space was rented in a Milwaukee Avenue plant. But the new plants were not enough. Auto manufacturing machinery moved out. Almost none of them could be used. They waited in their skins of grease undercoverings for some future day. Meanwhile, Packard engineers were working round the clock, redrawing to American production needs more than 2,000 English left-handed blueprints. Additional thousands of jigs and fixtures were specified for the gigantic shop task ahead. Then were installed the giant, medium, and midget machines of mass production. Here's the 48-spindle Bosch, reaming its 48 holes with a single operation. The drill presses make holes as fine as the point of a needle through metal hard enough to withstand the shock of an explosion. Yes, they're women. At that time, almost half the Packard payroll was women. Before the war, they didn't number 1 in 10. They were another part of our answer to the incredible expansion. A woman's light touch has helped in the inspection of parts so delicate they must be handled in tissue paper. A drop of acid perspiration can etch and eventually crack a piece of metal. When a few 100,000 machines, gauges, and instruments had done their jobs, the parts flowed into the main assembly line. 10,000 parts for a Packard Marine engine, 14,000 for a Rolls-Royce. One engine is enough to make your brain whirl, but here they come, like elephants in a circus parade, head to tail. An icebox full of dry ice cools parts before fitting into place. When warm, they expand to a tighter-than-perfect fit. The line moves too fast for one huge factory to supply all its parts. Some are farmed out to smaller shops and factories. The exhaust stacks of the test building are visible proof of the careful check being made inside, for it's never enough to just make this engine. You can't be content because it runs. Will each one keep on running under the stress and strain of battle action? The answer lies in arduous open throttle tests. So put gauges to its vitals, run it under its own power for 6 hours and see. Then, after this dynamometer test, every engine is taken apart, washed, cleaned, inspected, and put together again. The U-shaped tear-down and reassembly line on and within which all this happens is another one of the Packard firsts. To the layman, all seems confusion, but actually every move is purposeful, thought out to that ultimate efficiency necessary for the handling of such a complex machine in mass production. When an engine has been brought to that kind of condition, off again, on again twice, the least you can do is protect it. Wrap it up in super cellophane. Pack it in a vacuum with moisture-controlling crystals, because that engine deserves the best. Ready to go, it rests in a weatherproof box, and our job is done. That's what we thought when the bottom was kicked out of the world Americans were trying to live in. Men went to war, labor was hard to get, war materials grew scarce, and we were asked to increase our production of marine engines threefold. Only 47 engines in the Rolls-Royce contract had been completed of the thousands to come. More space, more employees, more women at work, and improved mass production helped, but never enough. Our management labor Work to Win campaign, conceived a month after Pearl Harbor, attacked the problem from inspirational, educational, and competitive angles. Its most successful outcome was the suggestion box. Employees of all departments could do their bits toward improving production. In a little over 2 years, Packard's people made 31,331 suggestions, over half of a mechanical nature. Some 5,000 were put into effect in the shops. Fred Ospedale, an aircraft engine assembler and gang leader, was invited to the White House to be honored for his innovations. Awards were given by the War Production Board to 156 Packard employees for production shortcuts useful on a national scale. Tens of thousands of Packard workers put their minds to cutting engine cost and the taxpayer's bill. Pooled together, the sum total of production spirit was greater than the individual contributions. It all adds up to nearly 70,000 engines for hot airplanes like this, for mighty midgets like these. We have the deep satisfaction of knowing that no builder such as Elco at Bayonne, who turned out the greatest share of the Navy's PT craft, ever had to wait for an engine. And 3 of our marine engines go into a single PT boat. Lieutenant Commander A.R. Montgomery, commanding officer of a torpedo boat squadron, said, "It is an inspiration to see where the Packard marine engines are built. And it is mighty reassuring to know you're backed by these engines when in action against the enemy."
Lieutenant Commander John D. Bulkley of They Were Expendable fame told how his PT boat engines in the Philippines and off New Guinea did 4 times the service normally expected of them. He said to a Packard group, "Your work has helped save my life and that of my crew many times. If the engines had failed us during any critical moments while at close quarters with the Japanese, I wouldn't be here today." With Buckley, as with all others in the PT boats, the one requisite was speed. And what went with it? Dependability. The boat skimmed the water like a seaplane taking off. They bounced from wave top to wave top. They dodged attacking planes. They played tag with enemy gunfire in a game that was for keeps. Can you imagine the men in those boats failing to feel gratitude for the power that helped them win their bets against death? As it was with the Marine engines, so with the Packard version of the Rolls-Royce.
It reminds us of the thousands of precautions we lavish on our engines to guarantee that they're perfect and will remain so under the most difficult conditions. This Magnaflux ferrets out metallic flaws invisible to the naked eye. The oscillograph uses electric waves to test for balance and freedom from the vibrations that increase dangerously with wear. New bearing materials of silver, lead, and indium have taught the engineers how to increase the lifespan of engines, be they air, water, or ground. Most spectacular of the many new heat-treating methods which burn greater endurance into materials is the night-riding oven. These and many other processes, inventions, and refinements helped fill in the great panorama of Packard at war. They spell better product, longer life, lighter, stronger, more powerful, and more efficient. This means we will be able to give you more for your money. These efforts foretell an auto of the future that will be benefited in every respect. Any young pilot or PT man wanting a post-war Packard because his service taught him to doesn't have to depend on that alone. He could ask one of the people who own a Packard Clipper bought before the war and still going strong. Their endurance is a guarantee of the continuity of the Packard effort. But the young man doesn't need to ask. When a man or machine is battle-tested, that's final. When men have bet their lives and won on Packard-built engines, it's not luck. It's a habit. It's the habit of precision manufacture, too strong to break down come war or mass production. It's the teamwork of Packard people who stand shoulder to shoulder for the best in war or in peace.
When in 1938 war clouds were gathering over the continent of Europe, the Rolls-Royce factory in Derby assumed a new importance. Home of the company since its inception in 1906, it was from here that one of the United Nations' greatest contributions to victory was brought to fruition, by a picked group of designers, engineers and executives under the able leadership of Sir Arthur Sitgreaves and Mr. E.W. Hyves. Inspired by the tradition handed down by the late Sir Henry Royce that only perfection was good enough, management and workers set about the task of further developing an aero engine which would enable the air forces of democracy to sweep the enemy from the skies and bomb his industries into submission. This engine was the Merlin. Away from imminent danger of air attack, an unobtrusive country house set deep in the Derbyshire countryside sheltered the Rolls-Royce Aero Planning Department. Here, engine designers worked under conditions of highest secrecy on the development of the Merlin engine, armed with data and experience gained from previous engines. The main characteristics of the new engine had already been decided in theory by the Engine Development Committee at Derby, and now began the task of calculating main dimensions and producing the plans for quantity production. At the same time, scale models of complete engines and power plants were made of wood in order to visualize and check the exterior dimensions, while much time could be saved in checking the dimensional suitability of modifications. Matters like frontal area, engine weight, working of retractable undercarriage, position of center of gravity could all be deduced from measurements and behaviors of these models. Next step was the making by skilled engineer draftsmen of many thousands of detailed working drawings, which would constitute the basis for building the prototype. As these drawings had in turn to be duplicated for use in the workshops, a blueprint department with an average output of 6,000 drawings a day was brought into being. At the experimental shop in Derby, emphasis is on the man rather than on the tool. Versatility is the keynote. Every job is different, and the men in this shop are among the most skilled workers in the Rolls-Royce organization. Soon the first components begin to take shape. In the experimental shop, the tool equipment is less specialized than that of the factories on production work, as it is concerned mainly with one-off jobs. Where duplication is necessary for parts like connecting rods, a Keller machine is used. The cutters are made to follow a master template, producing several identical pieces at a time. Few jigs and fixtures are available in the experimental stage, so the alignment of a machine surface is checked on the marking off table. A new engine is seldom built complete at first, so that although the production engine may have 12 or 24 cylinders, the first experimental job may only consist of one section of the crankshaft. And from this single-cylinder engine comes the first positive information. From these results, a forecast of the behavior of the full-size prototype can be made. When the prototype is assembled, it goes to the test house. The engine is coupled to a dynamometer, which is a form of water brake, which absorbs the entire power output of the engine, and is capable of adjustment so that the characteristics of the engine at different loads and speeds can be measured. The control panel also has fuel consumption, boost pressure, oil pressure, coolant temperature, engine revs, power output, and many other quantities. Ever since it was first developed, the rated horsepower of the Merlin has steadily increased. The later types have a power output 2 or 3 times as great as that of the original prototype, without any great change in leading dimensions. After test, the prototype is stripped down, and its parts are subjected to minute inspection. Parts which show signs of undue stress or wear are examined by the chief engineer and designers, who decide what alterations in design, manufacturing methods, or materials are necessary. Once the prototype has passed its first test bed trials, it undergoes further tests with the air screw fitted. Finally, it is ready for its flight test. Installed in an aircraft fuselage, the Rolls-Royce test pilot takes off to confirm that the Merlin engine will in practice do as much and even more than the designers had planned. Realizing that quantity, as well as quality, would be the need of the day, the Air Ministry asked Rolls-Royce to build a large factory away from Derby for the quantity production of Merlin engines. In 1938, work began on the erection of a large ultra-modern plant at Crewe, while in 1939, as war became a certainty, the company were asked to build yet another factory about twice the size of Crewe. Glasgow was selected, and work commenced on the Glasgow plant in July 1939. By early December, the first machine tools were already in production on the Merlin. In laying out the various factories for quantity production, the problem of the most efficient placing of machines and processes was solved by making planned silhouettes to scale of each machine and item of workshop furniture. These silhouettes were then manoeuvred on a scale floor plan until the ideal disposition was found. The layout was then photographed, and copies were sent to the plant engineers. As soon as all the machines were installed, full-scale production on Merlin engines commenced. Producing the Merlin engine in vast quantities without losing anything of the world-renowned Rolls-Royce qualities of precision workmanship presented untold obstacles. Apart from the difficulties of operating under wartime blackout conditions and the demands of the fighting services on road and rail transport, making difficult the movement of raw materials, there was the problem of labour. To overcome the manpower difficulty, training establishments were set up in various parts of the country. Under the tutelage of skilled Rolls-Royce craftsmen, both men and women were given intensive training in the operation of highly specialized machine tools in a section of the factory specially equipped for this purpose. In order to increase the supply of engineering draftsmen, experiments were made in training women of suitable educational qualifications. Inspired by the firm's tradition, these women eagerly proved their aptitude for this exacting work, and large numbers graduated to works drawing offices at the various plants. Apart from training men and women for aero-engine production, the company was faced with the problem of housing and transporting them to and from work. At both Crewe and Glasgow, housing estates and hostels were built within sight of the plant to shelter the workers who had come from all over the United Kingdom. In view of the fact that in Glasgow alone over 1,500 houses had been built, the local transport companies were called upon to cooperate in organising 126 special bus services to and from a depot inside the works itself, enabling the workers to get immediate transport to outlying districts. To protect the factories against air and ground attack, strong Home Guard and civil defence detachments were formed, made up of volunteer workers from the various plants. Fire brigades, also manned by workers, soon reached a high degree of proficiency and were equipped with motor pumps and all the latest firefighting appliances. The Rolls-Royce organisation was possibly unique in having its own bomb disposal unit, equally prepared to play a vital and dangerous part in an emergency. In order to safeguard the workers' health, an efficient medical organisation was brought into being. All new workers were given a medical examination and eyesight test, while surgeries and restrooms, staffed by resident doctors and nurses, were a feature of each plant. In order to ensure maximum cooperation between workers and management, joint production committees were formed at each factory, consisting of representatives of the management and representatives and shop stewards of the workers. Vast stocks of raw materials were built up, and a sample of every piece of incoming bar, tube, rod, or forging was sent to the laboratories for analysis. Each batch of material was given a number which stayed with it through every process, and a sample was taken so that a fault developing at any time during the component's history could be traced back to the raw material stage. Some of the most valuable raw materials were the light metal and other alloys discovered and developed in the company's research laboratories at Derby. Apart from the famous RR50, used in the manufacture of castings, many other equally important contributions to the Allied war effort were made by the pick of scientists and technologists working in these laboratories. In the Rolls-Royce drop forge shop, alloy steel forgings were pounded out night and day. The most highly stressed components of the Merlin engine are made from these forgings. which allow a very high output of accurately formed parts, while the metal itself, due to its molecular flow under the blows of the forge, becomes more homogeneous and capable of withstanding higher strains. In the manufacture of the Merlin engine, the light alloy foundry at Glasgow is unique in the Rolls-Royce organization and probably in the world. The foundry, with its core, moulding and fettling shops, occupies 2 entire blocks of the factory and is organized, like the rest of the plant, on a flow production basis. The layout of the foundry and its organization for production constitute a great feat of technical planning. Every kind of casting used in making Merlin engines is produced here. Very many difficulties had to be overcome on the material side of the process, and the achievement is made more remarkable by the fact that many of the workers are trainees, a large proportion of them women. Core making is a process which illustrates the way in which complex operations normally requiring much time and a high order of skill have been rendered rapid and certain in the hands of trainees of both sexes. The lighter cores are made by hand and mainly by women, on core tables to which ready-mixed sand is delivered by an overhead conveyor system. All the 300-odd intricate cores which go to each engine are made in the same manner. Organization has made each individual job simple. Men make the heavier cores by machine. A number of heavy cores are used in the upper half of the crankcase mould to form the bearing webs. This is one of the 2 main moulding bays, which are arranged on either side of the line of furnaces. The moulding machines are mostly of the rollover jolt type, both hydraulically and pneumatically operated and very simple to control. This mould, for the upper half of the crankcase, is the largest on the engine. Complete with cores and moulding box, it weighs a ton. The number of cores in the mould are an indication of the intricacy of the casting. This mould of the upper half crankcase, although the largest, is by no means the most intricate in the engine. The aluminium alloy, principally the famous RR50, is melted in gas-heated tilting furnaces adjacent to the mould conveyors. The larger moulds are poured from 2 sides simultaneously. This allows the use of ladles of manageable size and also tends towards an even temperature of metal throughout the mould. Very many and very large risers are employed to ensure sound metal in the casting. Castings are fettled in this bay with power saws and pneumatic hand tools. The first job is cutting off the runners and risers. On large castings, these are very massive, and a special type of twin-hand circular saw has been developed to do the job. The saws cut into the surplus metal from both sides so that it can be easily broken away at the end of the cut. Final fettling of the castings is done with pneumatic chisels. These cut away all the flash and webs which are not needed in the finished casting. Every casting is inspected before it goes for heat treatment. Before the castings are machined, they undergo heat treatment in this 88-feet-long priest furnace. The castings are loaded onto bogies, which are pushed into the front end of the furnace. This automatically pushes out a completely heat-treated load at the other end. It has 3 heat zones, and the temperatures are automatically regulated within plus or minus 2 degrees centigrade. Very many Merlin castings are produced by die casting. Metal moulds, or dies, are used in this process, which thus effects a considerable saving of time, since the same mould can be used over and over again. The die castings are taken away on the conveyor for heat treatment in the same way as sand mould castings. These die castings can be made to much finer limits than can ordinary sand castings. The surface is smoother, and because no gases are evolved in the mould, the metal is usually more homogeneous. The castings go to the machine shops for finishing. During the last few decades, amazing progress has taken place in the development of very elaborate and complex machine tools, both automatic and semi-automatic. Even in the hands of trainees or unskilled operators, these machines can and do perform the apparent miracle of producing in vast quantities the most intricate parts with the highest degree of precision. Actually, many men and women classed as unskilled or semi-skilled have become highly skilled and proficient in working a particular machine or operation, but the term is still used to distinguish them from the fully skilled Rolls-Royce operator. Operators, such as those at the Derby Works, have served a long term of apprenticeship, and schooled in the Rolls-Royce tradition have become qualified by this skill and experience to set up any machine and make the many adjustments necessary to keep it producing accurate work in the hands of trainee operators. Many of these machines have actually been developed by Rolls-Royce engineers, and such is the final simplicity of operation that although a skilled man would need vast quantities of complex drawings to make the parts by hand, these company-developed machines can be handled by comparatively inexperienced trainees, while still retaining the rigid Rolls-Royce standards of precision. The crankshaft is probably the most highly stressed component of an aero engine. Over 140 separate machining operations are needed to produce the Merlin crankshaft. For these processes, a large number of special-purpose machines were developed by Rolls-Royce, including vertical and horizontal automatic lathes, deep drilling and grinding machines, and these crankshaft lapping machines. The rough crankshaft forging weighs 250 pounds. In its finished condition, the shaft weighs 108 pounds. The connecting rod is another highly stressed component of the engine, and over 160 operations are necessary to produce a completely articulated pair. After every machine operation on a Rolls-Royce component, the part is subjected to careful inspection before passing on to the next operation. Women proved themselves to be particularly adept at this exacting work. There are over 11,000 parts in a Merlin engine, and a high proportion of the smaller items are made from bar material on automatic and capstan lathes. Except for tool setting, this work is repetitive, though quite an amount of skill is needed to be a good operator. Nevertheless, the consistently high output figures on close limit work to Rolls-Royce standards, achieved by trainee men and women who previously had no experience in the engineering industry, is indeed a remarkable achievement. Some 90 different types and sizes of gear wheels go into the Merlin, and all must be produced to exceptionally high standards of accuracy. Accurate tooth form and perfect structure of the metal itself is vital to the smooth running of gearing. A special gear analyzer is used for measuring the tooth forms of helical gears. This apparatus traces an enlarged graph, showing any departure from the theoretically perfect form. Great care and thought were devoted to the development of valves and valve springs. Machined from forgings, the first valve-forming operations are done on turret lathes and automatics. The heads and seating faces are covered with a special heat-resisting nickel-chrome alloy, applied in the flame of an oxyacetylene glow lamp. Exhaust valves are made with hollow stems and are half-filled with sodium, which melts at a low temperature. When the engine is running, heat is transferred from the head of the valve to the stem by the sodium splashing up and down. Valve springs are made from coils of high-tensile steel wire in a specially designed machine which coils valve springs continuously and automatically cuts them to length. After grinding and finishing, the springs are tempered in a special furnace. The journal and big ends of the Merlin run in bearings of a lead-bronze alloy. The bearing shells are made of steel, into which are inserted casting tubes, secured by spinning their lower edges over in a lathe. After the shells have been preheated, the lead-bronze alloy is cast from a parametrically controlled electric induction furnace. The poured liners are then placed in a special cooling device, consisting of a cylinder with jets of water spraying inwards. The rotor of the supercharger is outstanding among the light alloy components of the engine. This component may be called upon to run at between 20,000 and 30,000 revolutions per minute, corresponding to a peripheral speed exceeding the velocity of sound. It is, therefore, in the highest degree important that this rotor should be perfectly balanced. This is achieved by machining it all over. There are countless machining and finishing operations involved in the manufacture of thousands of other Merlin engine components. To each of these, unstinting thought and care were given in devising machines and machine tools capable of producing the required rate of quantity output without losing anything of the traditional Rolls-Royce quality. In order to ensure that the standards of manufacture were being maintained, Rolls-Royce engineers developed many high-precision measuring gauges and other complicated items of inspection apparatus to augment and improve the standards of normal engineering precision gauges. Inspection of each of the 11,000 Merlin components, not once but many times, was continuous throughout every stage of manufacture, including a thorough final inspection when the parts were completed. Every factory has at least one air-conditioned, temperature-controlled standards room, in which the gauges and inspection devices used in the manufacture of Rolls-Royce engines are continually checked against standard gauges and precision comparators whose accuracy is of the order of 10/millionths of an inch. When the finished components reach the sub-assembly stage, the engine begins to take shape. The assembly process is arranged as a sequence of operations in the same way as the machining. The sub-assembly benches are arranged in lines between the finished part stores and the engine erection lines. The component travels along the assembly line through the hands of dozens of different workers who each add their part or do their particular operation so that the component is finished at the end of the line. Components like the Supercharger are built up separately so that they go into the engine as complete units. At the end of the sub-assembly lines is the engine assembly shop, where the sub-assemblies are delivered at convenient points and are put together to make complete engines. Engine assembly starts with the crankcase, which has had all its studs and cylinder holding down bolts fitted on the sub-assembly benches. The engine assembly line has a bench-height rail track down the center, which enables the work to be pushed easily from station to station along the line. A turntable in the track at each siding enables the engine to be run off the main line while fitting is in progress, leaving the main line free for the flow of work. At each station, a sub-assembly or component is added to the engine. As the engine passes down the line, it gradually takes form. The policy of specialization is applied here in the same way as in the other departments of manufacture. Each job is done by a crew who are specialists in fitting their particular component. This policy enables the workers to become expert in a short time. At the end of the line, the completed engine is vetted by an inspector who notes the numbers of individual components and assigns a new number to the whole engine. From now on, it has an identity. It is given a logbook in which all its subsequent history will be recorded, but meanwhile it is to be taken away for its first run on the test bed. Every Merlin is run on the test bed before it is passed into service. The Ministry of Aircraft Production prescribed very stringent tests for engines to be used in the RAF or the Fleet Air Arm, so several hours' run at the rated horsepower of the engine are followed by bursts at maximum power, while test engineers make careful notes of the engine's behavior. A certain proportion of engines which have satisfactorily passed their tests are nevertheless brought back and immediately stripped down. The running test demonstrates that every component is capable of doing its job. This strip down is to make sure that there has been no overheating or overloading, and to ensure, in short, that the engine will go on doing its job and maintain the standard of manufacture. Once more reassembled, the engines are ready for active service, but the job is not yet finished. Just before the war, it became apparent that in order to ensure the satisfactory installation of the engine and the consequent safety of the aeroplane's crew, it was necessary for Rolls-Royce to devote their engineering skill to designing the completely cowled power plant installation, ready for attachment to the aeroplane fuselage. This enterprise in tackling the complete power plant and developing it into a quickly detachable and interchangeable unit was acclaimed as one of the outstanding achievements of British aviation during the war. No survey of Rolls-Royce wartime service would be complete without reference to some of their many other contributions to the success of the Allied nations. Early in the war, it became obvious that the facilities which had been envisaged for the repair of damaged engines were going to prove entirely inadequate. and measures to remedy the position became of the utmost urgency. Rolls-Royce set about tackling this problem and had the satisfaction of seeing the figure of overhauled engines, which stood at a few hundred in 1939, rise to over 18,000 during 1944. The Rolls-Royce School of Instruction at Derby had trained nearly 17,000 people in the use and maintenance of Rolls-Royce engines and other products. Those trained included pilots, flight engineers and ground personnel of not only the Royal Air Force and the Fleet Air Arm, but of representatives of the air forces of most of our allies. Another interesting example of Rolls-Royce versatility was the development of a small-caliber 40mm quick-firing gun for use in MTBs and similar craft. The Merlin engine was also adapted for powering these high-speed motorboats. Then again, there was developed a modified and unsupercharged version of the Merlin, known as the Meteor, which was used to power the first prototype of a new tank. The effect of the extra power of the engine on the prototype tank was such that Rolls-Royce engineers were asked to collaborate in developing the tank itself. The fruits of this collaboration resulted in the famous Cromwell tank, which covered itself in glory on the dash from the Normandy beachheads to the Rhine.
The Rolls-Royce organization may well be proud of its contribution to victory. Workers, designers, engineers, management all fulfilled a vital role in Britain's days of need. Now they can once more turn their hands and their brains to the fulfillment of the needs of a world at peace. And this, indeed, they have done. For in October 1945, 2 months after the end of hostilities, it was a Rolls-Royce jet turbine that streaked across Britain's luring skies to claim the world's speed record of 606 miles an hour. What promises to civil aviation did this imply? What even newer principles of engine design and propulsion are now occupying the minds of the Rolls-Royce organization? For the world of science has much in store, and in the forefront of mankind's march onward will be Rolls-Royce applying to practice the newest and latest principles of scientific achievement.
The P-51 Mustang, the most dominant escort fighter of World War II. It helped blaze a trail from England all the way to Berlin for America's bomber force.
Of course, the Mustang was a revelation. It was the war winner.
Its creation was sparked by a mixture of genius and chance. The Mustang and its two-stage, two-speed supercharged Merlin engine were the end result of years of technological development. From World War I to World War II, each generation of aircraft went ever higher and faster. But the Mustang's marriage with the Merlin might never have happened. National pride delayed the coupling of these two great innovations. But a new, deadly German adversary changed everything.
The Focke-Wulf 190, this was really a top-notch fighter aircraft.
With the FW-190 terrorizing the skies of Europe, the British and American forces swallowed their pride and joined together to create the ultimate fighting machine. December 17, 1903. The Wright brothers' aircraft, the Wright 1, successfully takes off, initiating the dawn of aviation. Man had already taken to the skies with gliders and balloons, but this was the first time that an engine had propelled him into the air. The Wright 1's engine was a crude design by today's standards and put out 12 horsepower only. It was an inline engine, meaning that its cylinders, 4 in total, were mounted in a straight line, a layout that would inspire some of the most advanced piston-engined aircraft ever created. Though a simple design, the Wright engine was innovative. It was the first engine to make use of a lightweight cast aluminum crankcase. Every pound counted. With a heavier engine, the Wrights may not have made history that winter's day in North Carolina. Aircraft weight and power would continue to be important to the evolution of flight. World War I was approaching, and the newly formed air forces of the world needed reliable engines with enough power to sustain flight during operations. From France would come a new type of power plant to take the fight into the air, the rotary engine. Rotary engines operated differently than the inline ones used by the Wright brothers. The cylinders were arranged in a radial pattern rather than a line. When the engine was fired up, the crankshaft remained stationary, while the crankcase and cylinders rotated around it. A rotary engine had one giant advantage over the inlines of the era. It was much lighter, and thus gave a pilot better performance during combat or while trying to evade an enemy. However, the rotary engine was not without its shortcomings. It had poor fuel economy, as it was often run on full throttle. It also provided an unpleasant ride. Castor oil was mixed with the fuel mixture for lubrication, with the side effect of heavy fumes, smoke, and an oil shower for pilots. Turns with a rotary-powered aircraft could prove treacherous. As the whole engine rotated, it produced a gyroscopic effect. A turn to the right, at full power and low level, could end with the death of a pilot. Rotary-powered aircraft remained part of Air Force inventories till war's end, but they were gradually supplanted by the inline engine. Inlines based on the same principles as the one found in the original Wright plane kept improving in terms of power and performance. Between the wars and across the Atlantic, a new type of aircraft engine would emerge to dominate American aviation. The U.S. Navy was looking for aircraft to populate its fledgling aircraft carriers. Space on board was extremely limited, but aircraft with inline engines often had lengthy noses. Their engines, built with rows of cylinders, took up too much space on cramped carriers. Rotary engines, though more compact, had too many other weaknesses to be serious contenders for the role. There was, however, a third type of engine. Before the war, there had been limited experimentation with radial engines. At first glance, these appeared to be just like rotary engines. It's only when they are fired up that the difference becomes clear. In a rotary engine, the crankcase and cylinders rotate around the crankshaft. But with a radial engine, the crankshaft rotates while the engine block is static. Radials often weren't as powerful as inline engines, but they were less complicated. They were cooled by air rushing over the engine rather than through a liquid cooling system. This made radials less vulnerable to battle damage, which might rupture the coolant lines. Navy pilots who might have to travel long distances over the ocean to get to a target needed an engine that would be sure to get them home under any circumstance. Most importantly for the Navy, radials were smaller than inline engines, so a greater number of aircraft equipped with them could be stored on board their carriers. The Wright Aeronautical Corporation, a successor to the original Wright Brothers Company, used their aviation expertise to create the first reliable radial engine for the Navy, the J-5 Whirlwind. The J-5 was put on display for the entire world to see when Charles Lindbergh crossed the Atlantic in his Spirit of St. Louis in 1927. His flight solidified the reputation of the J-5 Radial as a dependable power plant. The budding airlines of the world were looking for engines to power their airliners and to bring their passengers across continents and eventually across the globe safely. Reliable radial engines seemed to be the ideal choice. Radials would power many of the principal airliners in the history of civil aviation, from the Ford Trimotor to the Boeing 247 to the Lockheed Model 10 Electra. Both the U.S. Navy and U.S. Army Air Corps would rely heavily on radial engines as they built up their inventories of fighters and other aircraft. In the 1930s, the U.S. had just one inline engine in development, the Allison V-1710, an engine that would one day power some of America's great fighters. At the time, relying on radials seemed a prudent decision, but in the years to come and in the battles ahead, it will leave the U.S. playing catch-up with their allies and enemies in Europe. In Europe in the 1930s, air forces and aircraft manufacturers were looking for speed above all else as they designed the next generation of fighters. Using streamlined designs and powerful V-12 inline engines, they pushed their aircraft to speeds over 350 miles per hour. Their inline engines were not only more powerful, they also helped to create more aerodynamic airframes. Their elongated shapes allowed for more streamlined designs as compared with radials. Inline engines may have been more vulnerable to attack due to their complex liquid cooling systems, but no matter how durable a radial engine is, speed kills in a dogfight. Inline engines were built to provide just that. It was from this European obsession with speed that some of the legendary fighters of World War II were born, including the Supermarine Spitfire, the Hawker Hurricane, and the Messerschmitt Bf 109. Beneath their elegant frames purred ever more powerful inline engines from Rolls-Royce and Daimler-Benz respectively. In the middle of 1940, the pilots of the RAF tested their mettle and the endurance of their fighting machines in some of the most spectacular air battles of World War II. Vice-Fuhrer Göring had promised to destroy the RAF and thus facilitate the invasion of Britain. Göring had at his disposal an armada of medium bombers protected by a deadly fighter force. The result of the Battle of Britain during those few vital months of 1940 is well known. There was a heavy toll in fighters and pilots on both sides. British and German engineers tried to squeeze every ounce of power from their engines. Any tiny advantage could be the difference between life and death. With Britain and her industry under direct attack, she looked to her old colony more than ever to provide her with desperately needed aircraft. Even before the Battle of Britain, the British Purchasing Commission had already been shopping for additional aircraft. The US's initial offer of fighters was not well suited for the high-altitude dogfights taking place over Europe. This was partially due to the American engines available. The US had concentrated on radial engine production instead of inline engines like the ones so popular in European fighters. They did have the Allison engine, the V-1710. Like the British Rolls-Royce Merlin, it was a 12-cylinder inline engine, but it had a complex turbocharger often difficult to fit into an aircraft. To boost power in the thin air at high altitudes, the Allison engine used the heat of its exhaust to power a turbine and thereby increase the airflow and power. One American aircraft, the Lockheed P-38, had the extra space needed to house the turbocharger. It was a big twin-engined aircraft to begin with and had space in its tail booms for the extra equipment. But given the size of the P-38, it wouldn't have fared well against nimble single-engine German fighters in a dogfight. America had other smaller fighters powered by the Allison engine, the P-39 Airacobra and the Curtiss P-40 Warhawk. In both cases, their manufacturers failed to include Allison's turbocharger. The P-39 had an innovative layout, with its engine situated mid-fuselage, behind the pilot. It was designed to house both the Allison engine and the turbocharger. However, a scoop built into the left side of the fuselage to cool the turbocharger was deemed too aerodynamically expensive. Both the scoop and the turbocharger were eliminated from the production design. this change crippled the aerocover's ability to fight at high altitudes. In the case of the P-40 Warhawk, a rugged single-engine airplane, the turbocharger was excluded from the design from the get-go. This limited its optimal altitude to just 15,000 feet, and thus relegated the aircraft to ground attack work. The British Purchasing Commission was still interested in the Warhawk, even with its limitations. They saw it as more of an Army support aircraft. However, the Curtiss factory was running at capacity and could not fulfill the order. With no suitable aircraft readily available for purchase, the Brits would turn to North American aircraft. The British Purchasing Commission proposed that North American build the Warhawk under license from Curtiss. But NAA President Dutch Kindleberger had a bolder plan. He guaranteed that he could create an even better airplane, using the same Allison engine, in less time than it would take for him to retool for Warhawk production. The Brits said yes, and the end result was an airplane that may well have changed the outcome of the Second World War in Europe. Back in Europe, Germany was looking for an aircraft to augment the Bf-109. In the Battle of Britain, the Bf-109 and Spitfire were closely matched. But the Bf-109 lacked the range to be highly effective in its escort role over Britain in the summer of 1940. The Luftwaffe had a twin-engined escort, the Bf-110. It had the range to be an excellent escort, but it lacked the maneuverability to defend itself or its charge in a dogfight. It also used two Daimler-Benz 605 engines, making it an expensive sitting duck for British interceptors. Looking for a quick solution to their escort dilemma, the Luftwaffe even considered having the 110s tow 109s into battle to conserve fuel. But in the long run, using two aircraft to perform the role of a single fighter was an even more wasteful solution. What the Luftwaffe needed was a dedicated single-engine aircraft to fill in for the Bf-109 on longer-range missions, and ideally something to give them a decided advantage over the British fighters of the time. However, the Luftwaffe wanted to have its cake and eat it too. They wanted a new fighter, but they didn't want to sacrifice any of the precious 605 engines meant for the Bf-109. To the consternation of the Luftwaffe, most of the new submissions for fighter designs from German industry were to be built around this very same engine. To solve Germany's escort woes, one man, Kurt Tank, Focke-Wulf's legendary designer and test pilot, did what was almost unthinkable at the time. Since the start of the war, British and German designers had relied upon powerful 12-cylinder inline engines to power their fighters. Tank dared to build Germany's next fighter around a bomber's radial engine. The air-cooled BMW 801 radial engine had plenty of power and had proven reliable in the Ju-88 and Do-217. But radials in a fighter were a rare sight in Europe. It was difficult to build as aerodynamic a fuselage to house them in as when constructing one for a slender inline engine. Though an unconventional design track, Tank saw two reasons for encouragement. Firstly, the National Advisory Committee for Aeronautics in the U.S. had already done research on improving airflow around radial engines. Over time, they had developed the NACA cowl, which at least helped to reduce drag. This was a simple ring which fitted snugly around the cylinders of a radial engine. It not only made the engine more aerodynamic, it also improved cooling. Secondly, Tank observed that the US and Japanese navies were employing several modern carrier aircraft, all with radial engines. Aircraft like the F-4F Hellcat and the Japanese A-6M Zero. The lightweight Zero had been almost unstoppable in the early part of the Pacific War. Tank had continued to explore ways of improving his new radial-engined aircraft and reducing the drag effect, although some say his greatest task was selling the radial idea to the ministry. If that was the case, the bureaucrats must have been quickly won over by Kurt Tonk's first prototypes. Given the designation the Focke-Wulf 190, and unofficially known as the Butcher Bird, the Luftwaffe's latest fighter was rushed into production. Fortunately for the Allies, the FW-190 arrived after the close of the Battle of Britain. In the summer of 1941, 5 Mark V Spitfires flying over the south coast spotted several radial engine fighters in German markings. At first glance, they were mistaken for US-built Republic Lancers. It was a deadly case of mistaken identity. The aircraft were, in reality, early model FW-190s. The Spitfire pilots who survived the ensuing battle lived to tell just how quickly their comrades had been lost. But Britain's greatest loss that day was not pilots or planes. The battle marked the day Britain lost air superiority to the Luftwaffe. The RAF had to do something, and fast. All eyes looked to Rolls-Royce, manufacturer of the Merlin engine, the power plant of the Spitfire, Hurricane, and so many of Britain's great planes. Although the company had the next-generation engine, the 12-cylinder Griffin, in development, it was well over a year away, more than enough time for Britain to lose the war. Earlier, there had been some thought given to modifying a few Merlin engines for experimental high-altitude work to be executed by a Wellington bomber. It was little more than an idea at the time, but in Britain's hour of desperate need, Rolls-Royce engineers worked night and day to test the concept. Merlin engines were already supercharged. An air compressor mechanically attached to the rotating camshaft increased the airflow to the engine, allowing it to burn more fuel and to boost performance. Rolls-Royce engineers had theorized that adding a second supercharger could give the engine even more punch during high-altitude work. Might a two-stage supercharger help the RAF reclaim air supremacy? The end result of the Rolls-Royce experiments was breathtaking. It was almost as if the two-stage, two-speed Merlin was an entirely different engine, when in fact it was just a modification. When the double supercharged aircraft, dubbed the Spitfire Mark 9, finally arrived in June of 1942, the RAF had a rare opportunity to test it directly against a captured FW-190. The test results were far different than the day a group of unlucky RAF pilots ran into a flock of butcher birds. The two aircraft were virtual equals in terms of performance. Captain Eric Brown, who had flown a captured FW-190, had a chance to test the new Spitfire 9 against the German aircraft in live combat.
I'd flown the 190 quite a bit, so I wasn't too frightened. I reckoned I knew what that aircraft could do, and I knew what my Spit could do, so I thought, well, I can handle this guy. Hoping he was somebody just out of training school, but no, I picked somebody who really knew what he was up to. And we had, I would say, a toing and throwing over France, but neither could get a draw bead on the other. We finally realized, as both of us, we run out of fuel. We waggled our wings at each other and departed. And I realized this was really a top-notch fighter aircraft.
The RAF had leveled the playing field with the Luftwaffe, at least for the time being. But what the RAF really needed was an aircraft to give them the upper hand. The new Merlin's greatest contribution to the war was still to come, when it was mated with an extraordinary aircraft of American design. Back in the U.S., North American Aircraft had continued to work on a Warhawk substitute, which met the specifications laid out by the British Purchasing Commission. They had specified that the airplane be powered by an Allison engine, that it cost less than $40,000, and that it be armed with 4 .303-inch machine guns. North American answered with the P-51 Mustang. It featured an advanced laminar flow wing for good aerodynamic efficiency and a wide gate undercarriage for safer landing. Pleasing to the eye and to fly, Although mainly at lower altitudes, the new arrival quickly gained respect from pilots and ground crews alike. There were some concerns about how the Mustang would fare should it be forced to ditch while crossing the channel. During a water landing, its air scoop, located beneath the fuselage, might flood the aircraft or cause it to overturn. Water tank tests at Saunders Row were initiated to perfect the techniques for ditching the aircraft. Around the same time that the RAF was getting the Spitfire Mark 9 ready for combat, and the FW-190 was dominating the skies, Rolls-Royce test pilot Ronald Hawker was tasked with the mission of evaluating all aircraft powered by non-Rolls-Royce engines. He was thoroughly impressed with the P-51A, save for its poor performance at high altitude. Like the P-40 Warhawk, it had an Allison engine and no turbocharger. Hawker pondered how the aircraft might perform with the new Merlin engine. The results on paper were phenomenal. According to Rolls-Royce's calculations, with a Merlin power plant, the Mustang would not only outclass any American aircraft, but even new Spitfires using the same engine. Oddly, Hawker had to push for the mating of the Merlin 61 and the Mustang, even though the double supercharged P-51 would have outclassed the FW-190 as well. Hawker finally arranged for the marriage of the two great inventions, and test trials confirmed his hunch. The Mustang was a war winner. The main challenge was to produce enough aircraft and engines to reclaim the skies of Europe. North American would tweak the Mustang design to accommodate the Merlin 61 engine. It was a much more powerful engine, so the original P-51A airframe had to be reinforced. As well, the three-bladed prop was exchanged for one with four blades. The addition of plumbing for drop tanks might have seemed a small change, but it would have a great impact on the air battles to come. Packard took up manufacture of the Merlin 61 engines in the U.S. They were designated the V1650s. Packard had arranged a licensing agreement with Rolls-Royce earlier in the war. Ford was originally slated to build American-made Merlins and seemed a perfect choice due to the company's industrial might. But Henry Ford was adamant that his company build defensive weapons only. North American's double supercharged aircraft, the P-51B and P-51C, first took flight in the spring and summer of 1943. Air Vice Marshal Paddy Harbison recalls when the Mustangs first arrived at his Spitfire squadron.
Well, of course, the Mustang was a revelation. It was a much more comfortable airplane than the Spitfire was. And I have heard people talk about the relative merits of both. They were both war winners. The Spitfire was built as an interceptor. It could outturn a Mustang and it could outclimb it, but it didn't have the legs the Mustang had. And of course, if you can't get to where the fight is, you're not too effective.
As P-51 started to arrive in Europe, the war was changing, and the Mustang was the perfect aircraft for the time. The U.S. was taking the war to Germany. They were bombing the German war industry out of business. The only problem was their bombers were being shredded by speedy German interceptors. The U.S. had hinged their hopes on the ability of their bombers to defend themselves by maintaining a tight box formation. When this strategy failed, they were in dire need of an escort fighter. The P-38 Lightning was simply not agile enough to take on the role. Then there was the P-47 Thunderbolt. It was an awesome radial engine fighter, more than capable of taking care of itself in battle. But it had two major flaws. It was expensive, and it lacked the range to take the bombers all the way to Berlin and back. The P-51Bs and Cs arrived just in time. They had been designed to carry drop tanks, and with the addition of a fuel tank behind the pilots, they had more than enough fuel to escort American bombers to Hitler's lair. The Mustang proved more than a match for Germany's FW-190 and Me-109. Slowly, American bombers closed in around Berlin. Suddenly, the Germans found themselves playing catch-up. Kurt Tonk's FW-19 with a radial engine found it difficult at higher altitudes where the bombers roamed. Tonk swapped its radial engine for an inline. The long-nosed aircraft was nicknamed the Dora.
The Focke-Wulf Dora, the later Dora, was a magnificent fighter with an engine change, not really any structural changes other than those to accommodate the engine. But what it meant was, here was an airplane that could keep up with the hunt as the years of the war progressed. So from 1942 right up to the end of the war, the Focke-Wulf 190 was in the top grade of fighter or fighter bomber.
The P-51 Mustang also continued to evolve as mechanics and engineers incorporated changes based on the feedback of pilots who had tested the plane in battle. Its canopy went through several permutations. The British swapped the original one for a sliding Malcolm hood, similar to a Spitfire's for improved visibility. The P-51D, the definitive version of the Mustang, had a bubble canopy, which offered 360 degrees of clear view. North American also upgraded the D's firepower. It had 650 caliber machine guns compared to 4 in earlier models, and it had solved the problem of gun jamming during hard turns. The fuel tank situated behind the pilot may have increased range, but it created other issues. The plane had poor directional stability when the tank was full. To counter this problem, engineers added a small dorsal fin in the D model. These and other improvements would help the Mustang blaze a path to Berlin for America's bombers. Reichsmarshal Hermann Göring, commander of the Luftwaffe, was quoted as saying, "When I saw Mustangs over Berlin, I knew the jig was up." When the European war had come to a close, the battle still raged in the Pacific. The Mustang was the best escort available, but even with its incredible range, it could not accompany an aircraft like the B-29 Superfortress on extended bombing missions over Japan. The expanses of ocean were too large. The engineers at North American struggled with the problem of stretching the Mustang's range. Their solution was a Zwilling or twin Mustang. By fusing two Mustangs together, they hoped to dramatically increase the range of the Mustang while retaining its excellent dogfighting abilities. The new Mustang, the F-82, had an incredible range, 2,000 miles. Though the prototypes were powered by Packard-built Merlin engines, the U.S. Army Air Corps was adamant that the production version be totally American-made. Unfortunately for the F-82, without Merlin engines, it was not the same aircraft. When fitted with the Allison V-1710-100, its speed dropped and high-altitude performance suffered. It was one of the few cases of a prototype outperforming the production model of an aircraft. By the time the F-82 was ready, Japan had surrendered, and the war was over. After the war, the P-51 continued to serve, while other piston engine fighters of the era went quietly into retirement. Though it was the dawn of the jet age, there was still a place for the Mustang in a variety of roles. Colonel Ray O. Roberts flew the Mustang during its second life.
At that time I was flying what they call the F6, which is a P-51 with cameras. Also had guns, and you could have the bombing and gunnery capability. And we participated in a post-hostilities mapping program. We mapped, revised all the Japanese maps, photographed, did aerial photography in Japan and Korea.
When the Korean War arrived, Mustangs which had been mothballed for long-term storage were suddenly being shipped across the Pacific on carriers. Unable to compete with the next generation of jet fighters for the dogfighter role, Mustangs returned to where they started. In Korea, Mustangs made excellent ground attack aircraft. They didn't have the speed of jets, but they had the endurance to make it from Japan to Korea on bombing runs. In Korea, the F-82 also had an opportunity to taste combat for the first time. F-82s flew strike, escort, and night fighter missions. The marriage of the P-51 Mustang and the Merlin 61 engine produced incredible results. It provided the Allies with an effective escort to pound the last nails into Germany's coffin. Perhaps the most amazing thing about the P-51's stellar career is that it might never have happened. If the Merlin and Mustang had never been mated at the suggestion of Hawker at Rolls-Royce, the P-51 might have had a humdrum career as a reliable ground attack aircraft, rather than an elite dogfighter. It arrived at the right time and the right place in history, just when the Allies needed an escort fighter. The P-51 was the end result of years of aircraft and engine development. Though jet-powered aircraft would supplant it, the impact of the Mustang and Merlin in military history cannot be unwritten or denied.
In 1923, Frank Whittle joined the Royal Air Force. The 20s and early 30s were the formative years of the RAF. It was small, select, highly trained. RAF aircraft followed the fashions of the day, no longer constructed of wood, it is true, but still fabric-covered, wire-braced biplanes, differing little in essentials from the machines that had fought over the trenches in the closing stages of the Great War. On joining the RAF as an aircraft apprentice, Frank Whittle was trained as an airframe rigger, a trade he was never in fact to practice, for on completion of the 3 years course, he was selected to a much-coveted cadetship at the then newly created RAF College at Cranwell, where he learnt to fly and was duly commissioned as a pilot.
So I first went solo on the Avro 504K, and then on the Avro Lynx, then from there to the Bristol Fighter, then the DH-9A, and then on to the Siskin in my last term.
To be an RAF pilot was in those days a most agreeable position for a young man, flying from neat grass airfields all graced with well-appointed messes, a chain of exclusive flying clubs stretching from Britain across the Empire. The biplanes of the 30s, like these Hawker Hearts, could achieve sea-level speeds of around 180 miles an hour. The fastest single-seater of the time only managed just over 200. But as they climbed into the thinner air, their performance dropped drastically, a characteristic of the piston engine propeller combination. Frank Whittle, while a cadet at Cranwell, had written a paper, Future Trends of Aircraft Design, in which he had predicted speeds of up to 500 miles an hour. This would be impossible to achieve with biplanes due to the drag inherent in their design, for however powerful their engines, the maximum speed of a practical biplane would be limited to around 250 miles per hour. The 1929 Supermarine S6 Schneider Trophy seaplanes were to prove the point. That year, their 2,300 horsepower Rolls-Royce R engines had enabled them to win the trophy at 340 miles an hour. Later, in 1931, with still more power, one of them became the world's first aircraft to exceed 400 miles an hour in level flight. Yet in a sense, the Supermarine S6s were a red herring. Their very success obscured the fact that their performance was very nearly the practical limit obtainable, a fact that Cadet Whittle had realized at Cranwell.
One of the things that I did was work out what I now know was the well-known Breguet equation, which indicated that if you wanted to fly both fast and far, you'd had to fly at such a height that it was quite beyond the and at such a speed that it was quite beyond the piston engine and propeller combination.
In Germany, Fritz von Opel had in 1929 constructed an experimental aircraft to demonstrate that powered flight without a propeller was a feasible proposition. Opel used a number of solid fuel rockets to power a glider. It flew just, but its maximum duration of 10 minutes hardly foreshadowed an aerodynamic revolution. Opel's experiments made no impression on the aero engine manufacturers, who continued to construct their heavy, intricate piston engines. They're now employing the new technique of supercharging, that is, using impellers, high-grade paddle wheels driven by the engine, to pump the petrol-air mixture into the cylinders in an attempt to maintain sea-level performance in the thin air of high altitude. However efficient the designers and metallurgists made the power plants, the weak link at high altitude, the propeller, remained. Searching for an alternative, Frank Whittle at first considered using a piston engine to drive a compressor, pumping air into a jet pipe with burners, but he rejected the idea as hopelessly inefficient, which indeed it was. That proposition had been one considered in his Cranwell paper.
I didn't have the complete idea then. I was just groping towards it. Then in 1929, the penny dropped, and the idea of the turbojet came to me.
But the principle of jet propulsion had been discovered much earlier, in 120 BC, by Hero of Alexandria. His engine consisted of two small jets angled from a globe of silver, fed by a boiler through supporting pillars. With pressure up, the steam jets propel the globe. Thus man's first known heat engine was jet-propelled. 1600 years later, Sir Isaac Newton formalized the effect as his third law of motion. For each action, there exists an equal and opposite reaction. And if James Watt's celebrated observation of the boiling kettle's lid had applied Newton's law instead to the spout, he could have invented the turbine. Like this simple steam turbine, the gas turbine which Frank Whittle proposed is extremely simple, having only two major moving parts. The compressor wheel on the left and the turbine on the right, both keyed to a single shaft and housed within a pressure casing. The compressor's impeller forces air into the casing, which also contains a number of combustion chambers in which fuel, kerosene, is continually burnt. The expanding gases resulting from combustion pass through the turbine, turning it at very high speeds, up to 17,000 RPM, before exhausting from the jet pipe with enough velocity, 1,000 pounds in the early engine, to push the aircraft forward in powered flight. In 1930, that was still all theory. Undaunted, Frank Whittle patented his gas turbine on the 14th of October in that year. The high-speed monoplanes, which could conceivably utilize a jet engine, now existed, at least in prototype. But Frank Whittle knew that to construct a practical gas turbine aero engine was going in many ways to be a much more formidable undertaking. The massive 36-litre Rolls-Royce engine, which had powered the Schneider Trophy seaplanes, had required the most intensive research, not only into the very special chemistry of the fuels, but also into the then unknown territory of high-pressure supercharging. Rolls-Royce, with the aid of the Royal Aircraft Establishment, finally, after a great deal of work, managed to achieve a supercharger that could efficiently compress the mixture to twice sea-level atmosphere, and that in 1929 was considered to be very good going indeed. Frank Whittle had calculated that for his gas turbine he would require a much larger and far more efficient compressor, working at 4 times that pressure. The calculations for the compressor were included in a paper which Whittle wrote to prove the case for the gas turbine. But none of the aero engine manufacturers were in the least interested in his proposals, at a time when meagre orders for existing engines were hardly sufficient to keep the firm solvent. One obvious conclusion drawn from the Schneider Trophy was that the days of the biplane were numbered. The Air Ministry was therefore experimenting with monoplanes like this long-range Fairey. To spend the money instead on exotic engines, which could at best take years to develop, was out of the question. So to cool his ardor, the Air Ministry posted their young inventor to the Marine Aircraft Experimental Establishment at Felixstowe to discover how a land plane behaved in water. Frank Whittle also made 47 experimental catapult launches. One was to prove memorable, for his passenger was thrown out but managed to grab hold of the tailplane as he left.
I took a quick glance over my shoulder and I saw there was a body on the tailplane, but I didn't know who was my passenger. Until I found I wasn't losing control entirely. I'd got the stick right forward, full throttle. I took a more collected look and saw that it was my passenger, who then was struggled round into a sitting position with his back against the fin wire. And when he saw me look round with his helmet blowing out and his cheeks blowing out, he gave me a thumbs up sign with his spare hand. The other one was holding onto the fin. And I saw him go, okay. I thought to myself, well, you may think you're okay, old boy, but we can't get down. Because every time I tried to pull the throttle back, I couldn't hold up his weight.
He couldn't turn either due to his passenger leaning on the rudder, which was embarrassing since a German liner was dead ahead. The question was,
could I get back onto the water before I flew into the side of the ship? I managed it. The German ship turned to port, which was taking a bit of a risk in those shallow waters. This was just off the Isle of Wight.
In the summer of 1932, Whittle was posted to an engineering course at Henlow, which he passed with 98% marks. He then went up to Peterhouse College, Cambridge, to read for a mechanical engineering tripos. During those 4 years of study in that biplane era, Frank Whittle deplored the lost opportunities and had, by 1936, begun to face up to the reality of the continued rejection of his gas turbine engine.
I began to think it was before its time. In fact, I allowed the patent to lapse. And then along came Dudley Williams, now Sir Rolf Dudley Williams, or at least he wrote to me first. And then I saw him afterwards. He said he thought he could raise some money to get the thing going. And he and a partner did, in fact, manage to contact a small outfit called, commercial bankers called Falcon Partners. And they agreed to put up some money. And as a result of that, Power Jets was formed in March of 1936. But before the company was actually formed, Falcon Partners agreed to place an order with the BTH for the manufacturing drawings of an experimental engine.
To this day, Sir Frank still has the original drawing board, which was in 1936 Power Jet's principal asset.
The first jet engine was drawn on that. The BTH first drawing I wasn't satisfied with, so I did a half-scale drawing on this board, and that was the basis of the experimental engine. Power Jets had no staff except me, and I was on loan from the Air Ministry as a squadron leader.
So the initial practical work was contracted out to the British Thomson Houston Company at their Rugby's steam turbine works, where gradually the strange engine took shape. Casing, combustion chamber, the impeller of the compressor, and the turbine. By the 12th of April 1937, the engine stood complete and ready for testing. The question nobody liked to ask was, would it work?
When we first tried to start it up, we certainly succeeded. I was on the controls, and we got the thing running up to 1,000 RPM, and I got a signal from one of the fitters that there was a light up in the combustion chambers, and I signaled for the speed to be raised to 2,000 RPM, which was done with an electric motor. And then I opened the main fuel control to get it going under its own power, and it certainly did. It accelerated out of control, and so did everyone standing around. Except me, I was paralyzed with fright. I thought maybe we'd got something which we couldn't control. It went up to about half full speed, up to about 8,000 RPM, and then fortunately stopped accelerating. The reason was that there was a lake of fuel had collected in the combustion chamber which we didn't know anything about.
On its second run, the engine seized solid at 12,000 RPM. It was rebuilt and then run up to 13,000 RPM, with, Sir Frank remembers, a noise like an air raid siren. After those early test runs, the BTH management, not unreasonably, decided that a move to a rather more rural location was perhaps desirable. In the village of Lutterworth, the company owned a derelict property known as Ladywood Works, the name being a great deal grander than the location.
Oh God, it was terrible. It was an old disused iron foundry. They were the rickety old floors. Old Whittle had an office right like a rabbit hutch, you know, and it was a really terrible place. It had one test bed, as I remember. I can't remember what the workshops were like, but it was a pathetic setup, really.
With delays caused by the move and the chronic shortage of everything, especially money, it took a year to rebuild the engine, which seized up, to be yet again rebuilt in its third and final form, to become the prototype of the engine which would eventually fly, with the 10 interconnected combustion chambers. These were to prove one of the most difficult components of the engine to get right. This is that original Whittle engine, the first in the world to run, now preserved in the Science Museum, London. Incredibly, in spite of being constructed from salvaged parts, it ran remarkably well.
It was getting up to speeds of about 16,500. By the time we were getting it to this stage, it had been through so many mishaps that it was really a heap of junk. And so when I look back on it, it rather surprises me that we got it up to 16,500.
That was in June 1939. By then the Germans had annexed Austria and the Sudetenland of Czechoslovakia. The Munich crisis of September 1938 had passed, and of the peace in our time, then predicted by Neville Chamberlain, just 3 months remained. Since 1933, when Hitler first came to power, the Luftwaffe had been training and growing, secretly at first, then openly, until by 1938 it was revealed to have achieved and surpassed parity with the RAF. There was to be little doubt as to the quality of the Luftwaffe. For example, the Stuka dive bomber, which was soon to spearhead the Blitzkrieg, and the Ju-88, conceived in 1935 as a Schnell bomber, a bomber with the performance of contemporary fighters. To counter the Luftwaffe expansion, the RAF began to rearm. In 1936, the prototype of R.J. Mitchell's Spitfire had flown, as had the Hurricane, and both were now in full production to re-equip the fighter squadrons of the RAF, many of which were to fly biplanes until mid-1939. In the 12 months' grace between Munich and the outbreak of war, the long years of neglect of the RAF were to some extent made good. By September 1939, Fighter Command was at last equipped with modern aircraft, backed by an efficient radar-based fighter control system, and was considered to be able to counter the Luftwaffe. However, if anyone at the Air Ministry had thought that the German aero engine industry might have made the transition from their turbo superchargers to a gas turbine and be producing a German jet, then their appreciation went unheeded. In point of fact, the Germans had already made that step. It was the experimental Heinkel 178, powered by a jet engine designed by a young physicist from Göttingen University, Hans Pabst van Oene, who in 1936 had approached Ernst Heinkel with a proposal to build a gas turbine. Heinkel agreed to provide the facilities and finances for van Oene to build an experimental turbine which ran on hydrogen. The turbine produced only 176 pounds of thrust, but it impressed Heinkel sufficiently for him to back the development of a flight engine. With the backing of a large aircraft factory, the engine, similar to Frank Whittle's, was built and bench-tested by the winter of 1938. On completion, the engine was installed in the specially built HE-178, which was ready by the 27th of August 1939 to make the world's first gas turbine-powered flight. Van Oene remembers the day well.
Well, we had a short airfield. Wartz had already, the day before, taxied the aircraft, and he thought he could make it. It was an early morning, slightly foggy, but only very slightly foggy. And he accelerated. It worked without any problem. He lifted up, and then we lost him because we went on straight, and we didn't hear anything anymore. And so we waited, and then 5 minutes, a very long time. Then he came back, then he curved around, and we wondered why he is not landing. And so we felt, oh, he feels very good there. But the fact was that he couldn't really see, because the glare of that fog, he said, was terrible. The sun came up, and when he wanted to land, it was such a glare he couldn't really exactly see the airfield. So he made several rounds until he could really safely set down.
Test pilot Vasitz, Heinkel and von Oene celebrated with a champagne breakfast, perhaps a little prematurely, for 5 days later Germany was at war. In stark contrast to the plenty enjoyed by von Oene, Frank Whittle struggled with his single battered engine and was in those last weeks of peace suffering from an early example of catch-22.
Because the power jets was on the point of going broke, the Air Ministry was very reluctant to place any contracts, you see. They thought the firm was too rocky. But we were getting small contracts, £5,000, and then they paid for the second reconstruction of the engine at about £2,400. And altogether, by the time the engine was showing signs of being worthwhile, we'd spent about £20,000 all told, private money and Air Ministry money. But the real turning point was when the Director of Scientific Research came to Lutterworth, where we were testing the engine, and saw it run up to 16,500 RPM, and he became, for the first time, completely sold. Up to that time, they'd been paying the money on the basis that the job was really long-term research.
One result of that official visit was that all of Powerjet's work became subject to the Official Secrets Act, which made raising capital even more difficult. But the Air Ministry had at least bought the long-suffering original engine and had placed a contract for a flight engine, the W1, to power an experimental aircraft which the Gloucester Company were to design and build, the Gloucester Whittle E-2839. But it was still on the drawing board when the Second World War broke out, and all that Powerjets had was a model. The war, at first, at least in Britain and France, called the Phony War, was soon to change, to become the reality of Dunkirk and the Battle of Britain. That summer, Frank Whittle and his small staff still had the problem of finding an established aero-engine manufacturer, for although the E-2839 had yet to fly, it now had a successor, a twin-engine fighter eventually to be named Meteor, to follow the purely experimental Gloucester Whittle. The obvious choice, Rolls-Royce, were like the other major companies fully stretched supplying aero-engines for war production. Another difficulty was Frank Whittle's concern that a big company might absorb Powered Jets, whose patent position was far from satisfactory.
The patent position was not strong, the first master patent having lapsed. We had several other patents, but I didn't think that the patent position was very strong. So we were looking for subcontractors who were not likely, as we thought, to start competing with us. And it's happened that the wife of one of our directors was a friend of the wife of a director of the Rover Company, and as a result of that, we invited the Rover Company to act as subcontractors to us, which they agreed to do. The Rover Company, I'm afraid, made a shambles of the job, and their behaviour was, I think, absolutely disgraceful. They were out to get direct contracts, which they succeeded in doing. They did all sorts of dirty tricks. For instance, they got permission from the ministry to be responsible for the drawings. Well, on one occasion, manufacturing drawings, on one occasion we asked them to let us have a drawing of the compressor casing, and when it came, we found that it was, you might say, a breach of copyright, because it was in one of a photostat of one of our own drawings, with all reference to power jets removed, as though it were a rover company drawing. But unfortunately for them, they'd left in the bottom right-hand corner the names of our draftsmen, so that it was pretty obvious that it was merely a photostat of our drawing. And after that, I became much keener on getting a Rolls-Royce into the picture.
The first Rolls-Royce man to visit powered jets was Stanley Hooker.
Well, it was in January 1940 when Hayne Constant, who was the Director of Engine Research at the Royal Aircraft Establishment, took me to Lutterworth to see the engine. I'd never heard anything about it before. Constant used to come to Derby to discuss the Merlin Supercharger with me. And one day he said, I'm going to take you to see this jet engine, which was secret at the time. No, I met Whittle, and then he showed me his engine and discussed it with me, described it and so forth. And I can't say I was an immediate convertee to jet propulsion. I hadn't really studied it sufficiently for that. But I must say that standing by his engine when it was running, and they used to run more or less in the open in those days, one always had a sensation here was tremendous power, you know.
Stanley Hooker's brilliant work on the supercharger for the Merlin shared common ground with Whittle's jet compressor.
Lutterworth wasn't very far away, of course, only 30 miles or so, and I, having met Whittle and got on very well with him from the beginning, I used to go and see him fairly frequently. In fact, I used to take him Merlin supercharger the results to look at, because you see, he had no tests of his own supercharger. There wasn't a plant big enough in the country to test it. So I used to take him these things, and we had a lot of discussion. And eventually, when his engine was running at about 1,000 pounds of thrust, I went to see Hives, Lord Hives, or Mr. Hives as he was at the time, and tried to persuade him to go to Lutterworth and see the engine. And he said, what does it do? And I said, well, it's giving about 1,000 pounds of thrust. Well, now, we were all used to horsepower. We knew the Merlin gave 1,000 horsepower more. And one must admit that 1,000 pounds of thrust doesn't sound much compared with 1,000 horsepower. And Hives turned to me and said, well, that's not much, is it? You know, they wouldn't pull the skin off a rice pudding, would it? And I went away and did a sum, went back to him and said, do you know how much thrust the Merlin gives in a Spitfire? And he said, no, how much? And I said, 1,000 pounds. And he immediately rang for his secretary and said, I'm going down to see this engine with Hooker on Sunday.
And what was Hives' impression?
Oh, he went down, he came, he saw, he was conquered, you know, it was literally that, really. He didn't say much, he walked around and Whittle described it all to him, gave him a proper tour. At the end of it, he turned to Whittle and said, I don't see many engines about, Whittle. He said, why haven't you got more engines? And Whittle said, well, I look at the facilities I've got. I can't get anything made, I can't get this, and I've got no money, and so on and so forth. And Hives turned to him and said, well, send us the drawings and we'll make the stuff for you. And we made quite a lot of components at Derby for Whittle to help him with his job.
The Battle of Britain was by then at its height. The epic victory of the Spitfires and Hurricanes requires no retelling here, but it is pertinent to ask, if Frank Whittle had been better supported, could a developed British jet have made any difference to the struggle? In the absence of German jets, probably not. During the battle, there was never a shortage of RAF aircraft, but of pilots, and the existing Spitfires and Hurricanes carried the day, which was just as well, because the Gloucester Whittle was not rolled out until the spring of 1941, fitted with a non-flight Whittle engine, the W1X, to commence taxiing trials.
It was really a lash-up engine, which is why we call it the W1X, W1 Experimental. And that was used for the taxiing trials of this aeroplane.
It was taxied at Hucklecote on the 7th of April 1941 by Frank Whittle. He opened the W1X engine to 13,000 RPM, but the grass airfield was soggy and the best speed obtained was a mere 20 miles per hour. The next day, Gloucester's test pilot opened up to 15,000 RPM, and it was clear that the flight engine should provide adequate thrust for flight. As it was, it would seem that the W1X also had hidden reserves, as witnessed by Bob Fielder.
Then the pilot, Jerry Sayre, did just a short hop on the grass airfield, jet-propelled. So it really was one of the moments of my life. And I might record that afterwards, one of the other pilots, Mr. Michael Daunt, said to me, "Thank God it flew straight." I said, "What on earth do you mean?" He said, "Well, we all thought it was going to squib around like a squib firework."
The W1X engine used for the taxiing trials was removed from the aircraft and sent to the United States, and the 1,000-pound thrust W1 flight engine was installed in the prototype. Ground running had proved that the W1 engine would have no difficulties providing the minimum thrust, around 900 pounds, required for flight. This unique colour film of the original E2839 was taken by a Power Jets engineer, Matthew Latham, after the first flight made at Cranwell just 40 years ago.
On the day, 15th of May, 41, the weather during the day was too bad for other than taxiing trials until the evening. And then Jerry Sayre just tweaked the end of the runway, ran it up to the maximum speed that the ministry would permit, which was 16,500, holding it on the brakes, let go of the brakes, and he was off in 600 yards and just disappeared from sight in the clouds, and was flying for about 17 minutes and then came in doing quite steep gliding turns as though he'd been flying the airplane for weeks.
There were depressingly few to witness the event, and the only known record of that historic occasion is a still photograph and a fragment of 16mm film shot in defiance of the Official Secrets Act by an unknown amateur. What are Sir Frank's memories of that day?
Well, someone sat me on the back and said, "Frank, it flies." And I suppose I was tense or something, and my comment was, well, that was what it was bloody well supposed to do, wasn't it?
The marked lack of official interest on the occasion of the first flight still rankles with Sir Frank 40 years on.
Only a group of, from Power Jets and a group from Gloucester's, and the group from Power Jets included the resident technical officer from the ministry. But there were no official representatives, and what I think was rather a scandal, there was no attempt to make any official films of the whole affair, and so no good film of those first flights exists.
By contrast, there exists excellent film of Germany's second jet, the twin-engined Heinkel 280. The construction and first flight of their original jet, the 178, had been so secret that not even the German Air Ministry had been aware of it. After the successful test flights became officially known, orders for 9 prototype 280s followed, with the promise that if satisfactory, substantial production orders could well follow. In a remarkably short time, von Ohain, backed by the full facilities of the Heinkel Works, had designed and built a new turbojet, which gave 1,250 pounds of thrust on the bench to power the new aircraft, itself in many ways a most advanced concept, which can claim a number of firsts. It was the first twin-engine jet, the first with a tricycle undercarriage, and the first to fit and later to use an ejector seat. The 280 was the second jet in the world to fly. The first prototype, this is actually the third, had flown from this runway at Marianair, the Heinkel Company factory airfield, on the 2nd of April 1941, 6 weeks before the British jet, the Gloucester Whittle, was to fly. It's instructive, therefore, to see the progress that could be achieved given adequate backing, and there is no doubt whatsoever that if Whittle's project had enjoyed the same facilities, the Meteor could also have flown by this time. Although the 280 achieved over 500 miles an hour and battered an FW-190 in mock combat, no mean achievement, it did not, for political reasons, go into production. Neither did von Ohain's engines. The sole Allied jet in 1941, the E-2839, was, after its inaugural flight, extensively used to test fly a new Whittle engine, the W2B, installed in the Meteor. The E-2839 proved to be capable of 440 miles an hour, with an absolute ceiling of 56,000 feet, fully vindicating Frank Whittle's early claims for turbojets. However, the Whittle W2B was to prove a most difficult engine to develop.
I think many members of the team wished that we had gone ahead with the W1 air-cooled engine, WWII, rather than pushing ahead with the more advanced W2 series of engines, because the W1 engine had flown successfully, 10 hours flying with a brand new aircraft, brand new propulsion system, and never with the engine covers open once. And that, I think, must be an all-time record in aviation.
That success of the E-2839 led in some ways to an over-optimistic program for the Meteor. The ministry required 1,200 Whittle engines and 500 airframes. The question concerning Frank Whittle was who was to produce the engines. Relations with the Rover Company were then so bad that S.P. Wilkes, the managing director, went to Rolls-Royce to see his old friend Ernest Hives.
Hives sent for me one day and said, look, we're going up to Clitheroe tonight, we're going to have dinner with S.P. Wilkes. He didn't say why. So off we went and we had dinner in the Swan and Royal in Clitheroe, old pub there. And after dinner, old Hives turned to Wilkes with his usual abruptness and twinkle in his eye, always did it humorously, really. He said, you know, you're making a hell of a mess of this jet job, aren't you? You don't get on with Whittle. And Will said, yeah. He said, well, I don't know what you're doing with it. He said, you grub about on the ground, you know. It's an aircraft engine, it's our meat, not yours. I'll tell you what I'll do. I'll give you our tank engine factory at Nottingham. You give me this jet job. And Will said, I should be glad to get rid of it. And so we got all the Rover facilities at Clitheroe and Barnoldswick.
And that memorable dinner got Rolls-Royce into the jet aero engine business.
In the light of subsequent history, it was a remarkable dinner altogether. It was one of those 5 bob ones, you know, wartime 5 bob dinners. I can't remember whether Hives paid or Wilkes paid. I expect Wilkes did. Old Hives didn't would pull that one over, I expect. But it was a fantastic deal for Rolls-Royce as things turned out.
Next day, the two men went to the Rover jet production factory that Rolls-Royce had just acquired.
And Hives looked around and said, this will do as the experimental shop. Forget about production. We've got to get this engine right first, and then we'll produce it as easy.
The resources of what was, and arguably still is, the greatest producer of aero engines in the world was now at the disposal of Power Jets, with foundries able to cast intricate parts in steel or high-duty alloys, virtually unlimited stocks of high-grade steels and other metals, together with a large and highly skilled workforce able to utilize to the full the facilities available. A certain urgency was now attached to jet engine production. Mosquitoes of the RAF photographic reconnaissance units had been bringing back disquieting evidence, wispy outlines of unknown delta-winged aircraft and scorch marks on the grass airfields at Lechfeld, Peenemünde and Rechlin, the German equivalent of Boscombe Down, where this photograph was taken. These scorch marks were known to have been made by experimental jet aircraft. They could well have been made by the Messerschmitt 163, a lineal descendant of Opel's amusing rocket glider. The delta-winged 163 Comet, powered by a lightweight, liquid-fueled Walter rocket, had been designed as an interceptor fighter and possessed a truly amazing rate of climb. In October 1941, the prototype had broken the existing world speed record at over 623 miles an hour on the edge of the sound barrier. Rocket planes apart, a new jet was being tested in Germany by 1943. It was the Arado 234 Blitz bomber, the only jet bomber to see service in World War II, which it did during the Battle of the Bulge. But fortunately for the Allies, the 234 had suffered from a common weakness of German wartime research: too little and too late. Hitler had banked on a short war. By the time it was clear that this was not to be, there was insufficient time to develop the promising early prototypes which in 1941, with victory scented, had been postponed. But there was another fundamental reason for delay. The Arado, for example, had been held up for 12 months, while the Junkers company under Dr. Franz were developing their jet engine, the Junkers Jumo 004. It was certainly an advanced concept, an axial engine, that is, the simple, reliable Whittle-type compressor being replaced by these multiple blades, a difficult engine to get right even today, but it was theoretically more efficient, presenting a smaller cross-section, important in high-speed flight. Two were fitted in Germany's most successful jet fighter, the Me-262. The first flight was from the Messerschmitt factory airfield at Liebheim near Ulm. The date was July the 19th, 1942, and the pilot, Flugkapitän Fritz Wendel, who, in the absence of a propeller slipstream over the elevators, had to apply the brakes at 112 miles an hour as he passed a white line across the runway. He was later to report, "Immediately I touched the brakes, the tail lifted. The turbojets ran like clockwork, and indeed seldom have I been so enthusiastic during my first flight of a new aircraft." In fact, the 262 was tricky. The first two prototypes had flown with piston engines. This, the third prototype, was the first to fly on jet power alone. It had engines which required very careful handling. Too much throttle and the turbines burnt out, or the compressor stalled. Another unpleasant characteristic of those early axial engines was a pronounced lag in throttle response, which called for a very carefully judged landing approach. After the 17-minute first flight, test pilot Wendel slipped past the Gigant gliders that had been constructed in 1940 for the invasion of Britain, with just enough power on for a perfect approach and touchdown. But the moment he closed the throttles, no doubt in some relief, both jet engines immediately caught fire due to excess fuel igniting in the jet pipes. The fires were soon put out, but they were an omen of long delays caused by Luftwaffe indifference, and later Hitler demanding that the fighter be capable of carrying bombs. There were other problems with the engine, and 262s were not to see action until October 1944 to intercept the high-flying B-17s of the U.S. Army Air Force. Out of 1,500 built, there were probably fewer than 100 262s operational and never more than 15 serviceable at any one time, all flying with engines that were so underdeveloped that more 262 pilots were lost in flying accidents than in action. Nevertheless, had they been available in sufficient numbers with an engine as well developed as Whittle's, they could have made even the losses to the U.S. 8th Army Air Force unacceptable. As it was, they joined the Luftwaffe's piston engine fighters in the great air battles over Germany in 1944, and 262s accounted for at least 100 American bombers shot down.
I say two at 2 o'clock. Watch him, Scotty.
At that time, the only operational Allied jets were 16 Meteor 1s powered by Rolls-Royce Merlin engines developed from Whittle's design. The aircraft were hastily converted from a training to an operational role for 616 Squadron, the first in the RAF to fly jets, to intercept the very fast V-1 flying bombs. The first jet versus jet combats followed during the summer of 1944, though, admittedly, they were a little one-sided. The first American jet, the Bell P-59 Air Comet, was powered by two General Electric engines which were American copies of a Whittle W1. The General Electric Company had built their version in just 4 months, but too late to see service. In September 1944, the Minister of Aircraft Production, Sir Stafford Cripps, visited Power Jets, and Whittle suggested the nationalization of the entire jet aero engine industry.
What I visualized was a single cohesive unit with Power Jets at the hub of it, you see. And I even thought it possible that I would be the chief engineer of the whole business, since we'd started it, and our engines were, in my opinion, still the best.
Sir Stafford came, saw, and confiscated. The only company to be nationalized was Power Jets itself, whose staff thus became civil servants. It was a blow to Frank Whittle, for with the end of the war within sight, the Miles Company had designed the M52, which was to have been Britain's first supersonic research aircraft, to be powered by a Whittle-designed engine, which would have been the first ducted fan. This and other projects were under intensive development. But the fate of the M52 project began a fashion to be followed by successive governments. In February 1946, when the design was 97% complete, it was cancelled, along with all the other advanced engine projects of Power Jets, which was to become simply a test facility for other companies' engines.
We were forbidden to design and make engines, and so that the people who'd started the whole business were robbed of the right to design and build engines.
Frank Whittle resigned from the board of Power Jets and retired from the Royal Air Force as Air Commodore. Most of his staff followed him and scattered throughout the industry at home and abroad. Thus, when the new shapes, some owing much to German high-speed research, were shown at the early post-war Farnborough shows, the major responsibility of British aero engine design and construction had passed to other hands. Frank Whittle's brilliant pioneering work was to give Britain its world lead in jet aero engine technology. It was, in the early post-war years, made freely available to all. Sir Stafford Cripps gave Rolls-Royce Means to Russia to found their jet engine industry and to power their MiG-15s over Korea. Britain's second jet fighter, the de Havilland Vampire, was begun during the war, but too late to see service. At the 1949 Farnborough, the de Havilland Comet was shown to the public. It was the world's first civil jet airliner, and although tragically flawed, was the herald of the jet age in which, sadly, Sir Frank Whittle was to take no practical part. Although knighted and rewarded, he remains bitter to this day.
Oh yes, I am. But most bitter about firstly the fact that the policy mismanagement delayed the use of the engine in the war. It did go into operation, but in quite a limited way. Didn't have any material effect on the war. I was bitter about that, because it needn't have been so. And but even more bitter about the removal of my right to design and make engines. And one consequence of that was that the ducted fan, which is now practically universal, a turbofan, was delayed for at least 6 to 10 years.
October 4th, 1941. Incredible as it may seem, these crates marked the start of the development of the first jet engine in America. They contained an experimental engine which was flown to the United States from Great Britain under great secrecy in the fall of 1941. This flight was the direct result of a conference in the Washington office of General Arnold a few weeks earlier. Here was the actual beginning of the jet story in America.
What? Give you the Whittle engine. Consult all you wish. Arrive at any decision you please, just as long as General Electric accepts a contract to build 15 of them.
These were the plans of the first turbojet engine that had been successfully produced by any of the Allies. They were the results of a long, hard struggle by England's group captain, Frank Whittle. He had worked toward jet propulsion in the face of many difficulties, and he had succeeded. The Air Corps felt that jet propulsion had tremendous possibilities, and the British Air Ministry made all their information available to the United States. The men of General Electric knew from their with the National Advisory Committee for Aeronautics that the essentials of a turbojet were a compressor and a engine.
I cannot overemphasize the secrecy and the importance of this work. We know that both the Italians and the Germans are working on jets. I hardly need tell you that they must not win the race.
General, given unlimited priority, we will have the first unit running on test in 6 months.
6 unbelievably short months in all to plan, design, and build the first American jet engine for a revolutionary new principle of flight. Yet these men were able to make this promise to their government in time of war because actually this problem was not new to them. It really began on the campus of Cornell University in 1903, where a young mechanical engineer named Sanford Moss was working for his PhD. He was engaged in research for his thesis on gas turbines. He and his work had been consigned to this little building because there seemed to be a certain amount of noise connected with it. Not to mention smoke and odd smells. When he had completed his work at Cornell and received his degree, Moss went to General Electric, where he joined other experts and continued his work. Later, they set up a research department to study turbines of all kinds, as well as compressors, pumps, boilers, and related equipment. By 1918, Moss and his fellow workers had accumulated a tremendous amount of knowledge in relation to turbines and compressors, and as a result, he was called to Washington. There, the National Advisory Committee for Aeronautics initiated work with Dr. Moss on a practical turbo supercharger, which the Air Corps hoped would increase the altitude performance of its World War I fighters. A gasoline engine runs on a mixture of air and fuel which burns in a cylinder. At higher altitudes, the atmosphere becomes progressively thinner so that the engine cannot get enough air to burn as much gasoline as it should for maximum power. The turbo supercharger simply adds a compressor to the engine, which packs or charges the thin air into the cylinders. This allows the engine to burn more fuel and deliver full power. The compressor is run by a turbine, which is turned by the exhaust gases of the engine. Moss's work on the turbo continued, and his improvements had a tremendous influence on aviation. In 1920, the Army established a world altitude record of 36,000 feet, proving the turbo with air so rarefied that the pilot became unconscious and fell almost 6 miles before pulling out. General Billy Mitchell's famous test, which demonstrated for the first time The tremendous importance of air power was actually made possible by Moss's turbos. Mitchell's plane had to come in at 15,000 feet in order to avoid theoretical anti-aircraft fire. To give a plane enough power to carry a 2,000-pound bomb at that altitude, Mitchell had General Electric turbos installed on new twin-engine Martin bombers, and the results made aviation history. With the beginning of World War II, the Air Force's interest in turbos was greatly intensified. They quickly became standard equipment on such outstanding aircraft as Republic's Thunderbolt, Lockheed's Lightning, Consolidated's Liberator, and old reliable, the Boeing Flying Fortress. The high-altitude daylight strategic bombing operations which destroyed the strength of our enemy in Europe would not have been possible without turbos. They have contributed immeasurably to the science of flight and continue to do so. They are used on some of today's finest piston engine planes. The most formidable weapon the world has ever seen was carried by a turbo supercharged plane. So in 1941, with a new but related problem, it was only natural for the Air Corps to again turn to the same organization and ask them to build the first American turbojet. And build it they did. At a series of secret meetings 1 month before the arrival of the Whittle engine, the project had been started with a small nucleus of key personnel. These men picked those they wanted to work with. However, in most cases, they did not let them know what they were to work on. There were over 1,000 men on the project, but less than 100 actually knew what they were making. Planning and assembly of the engine itself was segregated in an entirely separate building and heavily guarded 24 hours a day. Many of the parts were made in the regular Supercharger department, but as a further protection, the project was called a new type of turbo and simply given another production number, Type I. All the vast resources of the company were thrown behind the project. The knowledge gained in years of production and design of giant turbines of every kind. The research laboratory for special metals. The experience gained in the manufacture and operation of thousands of turbo superchargers. And the vast store of knowledge of the consulting laboratories. During the actual design and manufacture under D.F. Warner, these great resources led to the modification and improvement of the Whittle engine. For example, the English had trouble with turbine bucket forgings because of the high temperatures involved, but it was an old story to these men, and their long experience with turbos hastened the solution to this problem. Also, the English impellers had been giving trouble because of cracking, but skilled craftsmen were already making hundreds of thousands of successful impellers for all types of superchargers. American techniques of rotor balancing were very advanced and contributed greatly to smoothness of operation. Yet in spite of the diversity and size of the operation, there was not a single failure in security. Today we realize even more fully than the pioneers the almost incalculable importance of that first American jet engine, the forerunner of the engines that power the military planes of today. Yet those early workers seemed to sense the true value of their work, and it brought them together. There was a wonderful spirit of common purpose, of cooperation between the people who did the work, Britain, our Air Force, and the men of General Electric. In this atmosphere, the engine grew at an unbelievable rate, until at last the first engine, right on schedule, rolled under heavy guard into the test cell. Now they would see the results of 6 months of round-the-clock effort. But they would see much more than that. They would see the birth of the jet engine in America. They would see the first really radical change in air power since the Wright brothers' flight so many years ago. They would see the first faint beginning of a whole new era in the age of flight. That is, they would see it if the engine ran. Now all they needed was to see it fly. Meanwhile, under the same rigid secrecy, the Bell Aircraft Corporation had been designing, laying out and building the Aerocomet to be powered by the new engine. They too had performed miracles of production in a startling new field.
I can't get used to working on a plane without a propeller. Neither can I. I hope it flies.
There were a lot of other people who hoped it would fly too, from top brass to Joe Average Man walking along Main Street, USA. Of course, he wouldn't hear about this particular plane for 2 or 3 years, maybe never. But he's a guy who carries deep within him a hope and conviction that any plane America builds will fly. These are the original films of the first jet plane ever to fly in America. With that first flight on October 1st, 1942, less than a year from the start of the project, jet-propelled flight in America became a reality. They had gotten off to a flying start, but in a race, it's the stamina that counts. So everybody kept right on working. The original engine, the IA, delivered 1,400 pounds of thrust. It was soon followed by another engine with more power, the I-16 with 1,600 pounds of thrust. Then came the J-33 with 4,000 pounds of thrust, and the jet engine really came into its own. The first flight of the J-33 was in June of 1944 in a Lockheed F-80 Shooting Star, again less than a year from the start of the project. This outstanding plane set many records, such as coast to coast in 4.5 hours, and became our first operational jet platform. In order to get the jet industry moving and in the interest of national defense, GE passed along its plans to other manufacturers. Allison began mass production of the J-33 engine to help meet production requirements of the F-80 Shooting Star. The British Whittle engine and the first engines designed by GE used compressors of the centrifugal type. In these, air enters the hub and is hurled radially outward. However, even prior to seeing the British engine, work on an axial compressor had been started with the National Advisory Committee for Aeronautics. In this compressor, air flows in a straight line to the rear. The axial compressor increases the engine's efficiency and handles a greater volume of air without increasing the engine's diameter. Long-range research led to an axial flow J-35, which powered the Republic Thunderbolt, and the Douglas Skystreak, holder at that time of the world's official speed record of 640 miles per hour. 8 of these powerful new jet engines were also used in Northrop's 100-ton Flying Wing and many other planes in the rapidly developing jet field. During these years of progress with land-based aircraft, the Navy had worked with the McDonnell Aircraft Corporation and Westinghouse to develop the Phantom. Proof that problems associated with carrier-based aircraft were not beyond solution came with the Phantom's first takeoff and landing from an aircraft carrier. Meanwhile, a school was established at General Electric to train the people who would install, operate, and service their new GE jet engines. One of the courses given is simply a general familiarization with the principles of jet propulsion and the jet engine.
Ever since man undertook the conquest of the air, he has had 2 primary considerations. First, the aircraft itself, and second, its method of propulsion. Needless to say, he has not always been successful. Sometimes the airframe itself has been unsatisfactory. At other times, the method of propulsion has lacked the necessary power. In this case, for example, it's extremely simple. While in this, it's so complex that it borders on confusion. Actually, the early attempts at propulsion by reaction were not associated with aircraft. And, as in the case of most of man's early endeavors, they led to some rather startling results. The principle itself is very simple. Newton's third law of motion states that for every action, there is an equal and opposite reaction. For example, an ordinary rotary lawn sprinkler turns because of the reaction of the arm to the action of the jet of water. It does not turn because the water squirted out pushes against the air. It would spin just as well in a vacuum. Similarly, the jet plane flies because of the reaction to the jet. It does not fly because the jet pushes against the air behind it. The engine itself consists of two main rotating elements, the compressor and the turbine, which are both mounted on a single rotating shaft. Air is drawn in, compressed, and packed into the firing chambers where fuel is injected. The constantly burning fuel tremendously increases the energy of the enclosed gases, which rush through the turbine and out of the tail cone. The turbine, operating like a windmill, supplies the power to spin the compressor, the expanding gases pushing their way out of the rear at about 1,200 miles per hour, give the plane its forward thrust.
This, then, is the simple principle of propulsion which changed the whole outlook of the aviation industry. By 1951, GE's production models were delivering more than 5,800 pounds of thrust, a five-fold increase in 10 years. These engines are being mass-produced at both Lynn, Massachusetts and the great new Lockland, Ohio plant, the jet center of the world. Lockland represents more than huge production facilities. It represents a new production plan. Thousands of suppliers and subcontractors contribute to the manufacture of the jet engines which are assembled at Lockland. Thus, all sources of supply, down to the smallest individually owned machine shops, are benefited by the program and kept mobilized for production. The Lockland plan is truly another milestone. Just as the engines which rolled from its production lines are the end product of many milestones, the result of almost 50 years of the best thought and effort of executives, engineers, scientists, and skilled craftsmen doing the work they are best fitted for in their own way. This freedom of effort is, after all, the real heritage of all Americans, and the engines are living up to that heritage. Today, General Electric turbojets are doing their job powering the great new planes they were designed for. Such planes as the Republic XF-91, high-speed, high-altitude interceptor, the North American F-86D, the Martin XB-51 superfast tactical bomber, the North American Sabre, holder of the world's official speed record of 671 miles per hour at the 100-kilometer closed course of 635 miles per hour. The North American B-45 Tornado, the first operational jet bomber. Boeing B-47 Stratojet bomber, which at 9:49 flew non-stop coast-to-coast in 3 hours and 46 minutes. And the mighty Convair B-36, the intercontinental bomber, which is powered by 6 turbo-supercharged piston engines and 4 jets. These and others are the planes which must maintain the common security of the free peoples of the world and thereby ensure peace. And fame. In one 6-month period, 3 new GE engine designs were okayed for production, each powerful than the preceding one. The last of these is no larger than the model then in mass production, yet it delivers so much more thrust that it is not even in the same class. Even so, by the time any new engine is in mass production, still newer and better engines are on the way. Engines that will be a tribute to the life work of Dr. Moss, who died in 1946, 1 year after being awarded the Collier Trophy, aviation's highest award. Moss's work is finished, but there will always be others to carry on with new ideas. Perhaps we will travel from coast to coast in 3 or 4 hours of quiet, vibrationless comfort. Certainly our energetic and progressive aircraft industry will give us commercial jetliners as soon as the time is right. Even the atom may release its giant strength for aircraft. The Atomic Energy Commission, the Air Force, and General Electric are already cooperating on an atomic power plant for an aircraft to be built by Convair. NACA, the U.S. Navy's Bureau of Aeronautics, and a number of private corporations are also making real contributions to this program. Developmental engineering moves forward with great new facilities such as GE's Aircraft Gas Turbine Laboratory. Here, engineers can simulate conditions for tomorrow's aircraft. Here, men look ahead at the requirements of the planes of the future, requirements established by the product planners of the engine builders. of the airframe builders and of the aircraft users. These are the molders of aviation progress. As long as imagination, research, design, test, and mass production continue year after year in a never-ending, constantly improving chain, there is no limit to the future of the aircraft engine. And so the jet story grows. In 10 years, we have come from this to this. No one can foretell the tremendous strides the aircraft industry will make in the next 10 years. Yet we can be sure that the engines will keep pace. The engines that are keeping and will always keep America strong.